Hello there and welcome to Cosmos for Sleep. Tonight, we're embarking on a gentle journey through the ancient realms of comets and asteroids, uncovering 100 fascinating truths. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe, let your eyes grow heavy, and let's begin. Life's building blocks, such as amino acids, have been discovered on meteorites, subtly hinting at cosmic origins for life beyond our home planet. These complex organic molecules suggest that the delicate ingredients for life might be widespread throughout the cosmos. Gently carried by these ancient space travelers across vast distances, profound discoveries subtly hint at a universe where the fundamental components for life are not exclusive to one planetary cradle, but are widely distributed, patiently awaiting the right conditions to foster new beginnings. Beyond these delicate organic compounds, these cosmic visitors also played a foundational role in shaping our own planet. Scientists believe that the vast oceans and the very atmosphere, which now cradle Earth's vibrant ecosystems, may have substantially originated from the gentle impacts of ancient comets and asteroids billions of years ago. These icy visitors delivered their precious volatile compounds, gradually contributing to the formation of our planet's life-sustaining environment over eons. It is a serene thought that the water we drink and the air we breathe hold ancient ties to these distant, icy wanderers. While these celestial bodies brought life-giving elements, their interaction with Earth has also orchestrated moments of profound change. A majestic asteroid impact, for instance, is widely considered to have initiated a significant reshaping of life on Earth approximately 66 million years past. This particular event led to sweeping climate shifts across the globe, allowing for the tranquil rise of new mammalian species and the eventual flourishing of new ecosystems across the planet, a natural progression in Earth's long, evolving story. It was a cosmic influence that delicately reset the biological tapestry of our world. These silent cosmic wanderers, both comets and asteroids, hold deep historical significance. Comets, in particular, are often referred to as cosmic time capsules, their pristine, frozen cores preserving material from the very earliest moments of our solar system, nearly 4.6 billion years ago. Within their icy hearts lie delicate clues to the primordial conditions and the raw ingredients from which all planets, including our own, gently formed. They offer an untouched glimpse into the pristine beginnings of our cosmic neighborhood, a tranquil archive of creation. Asteroids, in turn, represent the resilient remnants of the early solar system, material that never quite coalesced into fully formed planets. They are often gracefully termed minor planets, serving as the rocky and metallic building blocks that gathered in the inner solar system, offering a silent, enduring fossil record of planetary formation's initial phases. Their diverse compositions speak to the varying temperatures and pressures that existed as our sun began its luminous reign, a collection of unfulfilled planetary aspirations drifting peacefully through space. Our solar system is cradled by two immense reservoirs of these ancient objects. Far beyond the orbits of the known planets lies the Oort cloud, a vast, ethereal, spherical shell of icy bodies. This distant, serene realm is believed to be the patient birthplace of most long-period comets, those celestial visitors that embark on journeys lasting tens of thousands or even millions of years. It extends far beyond the most distant worlds, a tranquil treasury of frozen fragments, patiently awaiting the subtle gravitational nudges that will begin their long, deliberate journey inward toward the sun. It is a region of profound stillness, where cosmic history slumbers. Closer to home, yet still beyond the majestic orbit of Neptune, lies the Kuiper Belt. This disc-shaped region is a bustling neighborhood of thousands of icy bodies, including several recognized dwarf planets, and serves as the gentle source of short-period comets. These quiet, icy worlds orbit the sun in cosmic solitude, their presence a testament to the colder, outer reaches of our solar system's formation. This zone represents a more immediate yet equally ancient collection of frozen worlds, each following its measured path. As these comets gracefully approach the sun, they unveil one of their most captivating features, their luminous tails. It is a fascinating observation that comet tails always extend away from the sun, irrespective of the comet's direction of travel. This elegant celestial alignment is due to the subtle, persistent push of the solar wind and the gentle force of radiation pressure emanating from our star. This creates a luminous, ethereal stream that gracefully flows outward, a silent and majestic banner unfurling across the dark canvas of space, a tranquil dance of light and energy that mesmerizes all who gaze upon it. The tale's graceful arc is a direct consequence of the sun's pervasive influence, a delicate cosmic beacon. To truly understand these celestial wanderers, humanity has embarked on remarkable journeys of exploration, extending our reach across the silent void. One such pioneering endeavour was the Rosetta mission, which achieved a significant milestone by successfully landing a probe named Philae onto the surface of Comet 67 P. Churyumov-Gerasimenko in 2014. This remarkable achievement allowed scientists to gather unprecedented data, offering the unique opportunity to study a comet's nucleus up close. Philae's instruments meticulously probed the comet's icy, dusty terrain, carefully analysing its unique composition of water ice, complex organic molecules, and various frozen gases like carbon dioxide and methane. The gentle touchdown and subsequent observations provided a tangible connection to an ancient, icy world, patiently exploring its secrets for a brief, yet invaluable period. The mission's findings illuminated the delicate interplay of ice, dust, and organic molecules that form the very heart of a comet, deepening our appreciation for these pristine relics and their profound role in the early solar system's intricate chemistry. This quiet exploration unveiled a world far more complex than a simple, dirty snowball, revealing a rich, varied surface shaped by subtle solar warmth. Not only have we visited comets, but we have also reached out to the asteroids to retrieve their ancient, unblemished materials. Japan's Hayabusa 2 mission, for example, meticulously collected samples from the asteroid Ryugu and gracefully returned them to Earth in 2020. This delicate feat provided direct and invaluable insight into asteroid composition, allowing scientists to examine these tiny fragments firsthand in terrestrial laboratories with unparalleled precision. These precious pieces of cosmic history carry invaluable information about the early solar system, perfectly preserved within their ancient carbonaceous structures, offering a quiet, tangible link to the conditions that prevailed billions of years ago. Each microscopic grain tells a silent story of cosmic evolution, a narrative etched in stone from the very dawn of our planetary system, providing profound clues to the primordial building blocks that eventually formed our world and its neighbours. The successful return of these samples represents a gentle triumph of human ingenuity, bringing distant cosmic history home. Continuing this quest for ancient samples, the OSIRIS-REx mission also embarked on its own serene journey, meticulously collecting a pristine sample from the asteroid Bennu. This invaluable piece of an ancient celestial body was then carefully returned to Earth, providing scientists with an untouched specimen for profound and detailed study. Such meticulously gathered samples allow for extensive laboratory analysis, gently unlocking secrets about the solar system's chemical evolution and the delicate origin of life's essential ingredients. By studying these carbon-rich fragments, researchers hope to understand with greater clarity how water and complex organic compounds were delivered to the early Earth, potentially fostering the conditions for life to gently emerge and flourish. These collected fragments serve as miniature cosmic libraries, holding profound answers to the universe's quiet, persistent questions about our own existence and the grand tapestry of cosmic life. Within the vast expanse of the asteroid belt, some objects stand out for their considerable size and unique characteristics. Ceres, for instance, is the largest object in this belt and is also classified as a dwarf planet, a distinction it earns due to its substantial mass, its gentle, rounded form, and its internal hydrostatic equilibrium. It is unique for its potential to harbour vast reservoirs of subsurface water ice, suggesting a more complex internal layering and geological history than most asteroids. This tranquil world, with its subtle internal dynamics, hints at a past where it may have once held closer ties to the larger planetary bodies, perhaps undergoing cryovolcanic activity that shaped its serene surface. Its presence is a testament to the varied forms that can emerge from the solar system's early construction, a small icy world retaining ancient water, a quiet celestial sphere in the midst of rocky fragments. Following Ceres in mass, Vesta is the second most massive object residing within the asteroid belt. It is remarkably bright, reflecting a significant amount of sunlight, and shows compelling evidence of past volcanic activity on its surface, indicating a differentiated interior with a distinct core, mantle, and crust. This asteroid offers a rare and precious glimpse into the internal processes of larger protoplanets that once existed in the early solar system, before their growth was halted or they were gently broken apart by cosmic encounters. Vesta's ancient geological features, including vast impact basins and flowing lava-like terrain, are a silent testimony to a time when celestial bodies underwent more active internal transformations before settling into their current, more placid states. Its bright surface is a gentle beacon in the asteroid belt, hinting at a dynamic and complex past, a cosmic fossil of early planetary formation. The distinctions between comets and asteroids, though generally clear, can sometimes subtly blur, revealing the rich and fluid diversity of small bodies in our solar system. Some asteroids, known as active asteroids, occasionally and unexpectedly display comet-like tails of dust and gas, creating a fascinating puzzle for astronomers. These celestial objects gently defy easy categorization, exhibiting characteristics of both rocky and icy bodies simultaneously. Their sporadic luminosity, likely caused by the sublimation of subsurface ice exposed through gentle impacts or rotational stresses, reminds us that the cosmos is full of subtle surprises and ongoing transformations. The boundaries between different types of celestial wanderers are not always rigidly defined, but can gracefully overlap, revealing a deeper, interconnected cosmic reality where ice and rock mingle in unexpected harmony. These hybrid objects underscore the dynamic nature of our solar system's smaller inhabitants, constantly evolving. Among the icy giants, Comet Bernardinelli-Bernstein holds a special place, representing a truly colossal example of these primordial objects. It is currently recognized as the largest known comet, with an estimated width of about 150 kilometers, making it substantially larger than many asteroids. Its immense size allows it to retain volatile compounds, such as water ice and various frozen gases. Even when traversing the vast, cold distances of the outer solar system for eons, far from the sun's warming embrace, it only becomes actively luminous, developing its characteristic coma and tails when it gently approaches the sun, releasing its ancient frozen gases into space in a grand, ethereal display. For most of its existence, this colossal comet drifts in profound stillness, a silent, patient traveller from the deep reaches of the Oort cloud, a magnificent, slumbering titan of ice and dust. It is a testament to the quiet, enduring nature of the outer solar system's ancient inhabitants, and as we continue our gentle cosmic drift, it's worth appreciating the unique compositions that define these celestial bodies. Comets, for instance, are often poetically described as dirty snowballs, a fitting term that beautifully captures their fundamental nature. Their nuclei are primarily constructed from a delicate mixture of ice, dust, and various frozen gases, including carbon dioxide, methane, and ammonia. This unique composition is what allows them to undergo a serene transformation as they draw closer to the sun. When warmed by our star's gentle embrace, these frozen volatiles do not melt, but rather sublimate, directly transitioning from solid to gas. This process creates their characteristic glowing coma, the hazy envelope, and their magnificent tails, a breathtaking display of cosmic artistry. In gentle contrast, asteroids present a different geological story. They are predominantly rocky or metallic in their composition, forged from the very same primordial material that eventually coalesced to form the inner planets of our solar system. These ancient fragments often contain a wealth of valuable minerals locked within their solid forms. Their diverse compositions beautifully reflect the varying conditions present during the solar system's early formation, ranging from the silicate rocks found closer to the sun to pure iron-nickel in bodies that formed in different thermal environments. This subtle variety offers a tranquil window into the planet-building processes that unfolded eons ago. Scientists have gently categorized asteroids into three main types, each revealing a unique chapter in the story of planetary construction. The C-type asteroids are known for their carbonaceous nature. They are typically dark in appearance and rich in carbon compounds, representing some of the most primitive material in the solar system. Then there are the S-type asteroids, which are stony, primarily composed of silicates and nickel iron, offering a glimpse into more processed materials. Finally, the M-type asteroids are predominantly metallic, consisting mostly of nickel iron, suggesting origins from the cores of larger, shattered celestial bodies. Each of these types provides a distinct and invaluable window into the different stages of planetary formation, a serene catalogue of cosmic evolution. As a comet draws near the Sun, it typically unfurls two distinct and mesmerizing tails, each a testament to different celestial forces. There is usually a straight, ethereal bluish ion tail and a broader, more diffuse yellowish dust tail. These luminous extensions are subtly shaped by the separate influences of solar wind and radiation pressure, gracefully revealing the intricate ways a comet interacts with its stellar environment. This dual display is a silent, elegant dance of light and matter, a transient masterpiece painted across the cosmic canvas. The ion tail, with its delicate, almost ghostly blue hue, is composed of ionized gas. These charged particles are gently pushed directly away from the Sun by the powerful, yet invisible solar wind. This continuous stream of charged particles from our star causes the gas in the tail to glow through a process known as fluorescence, creating its characteristic luminosity. This ethereal blue stream is a direct visual representation of the Sun's constant outflow of energy, a luminous pathway tracing the invisible solar breeze through the vastness of space. It is a subtle, yet profound connection to our star's pervasive influence. The dust tail, in contrast, is formed from countless tiny solid particles. These microscopic fragments are gently pushed away from the Sun by the subtle force of solar radiation pressure. As the comet continues its journey, this tail often appears gracefully curved, lagging behind the comet's path due to the particle's inertia. This gentle arc of light beautifully reflects the Sun's radiance, slowly dispersing microscopic remnants of the comet's long cosmic journey, scattering ancient stardust across the inner solar system, a tranquil trail marking its passage. Surrounding the comet's solid nucleus is a hazy, luminous envelope known as the coma. This expansive cloud of gas and dust can grow to truly astonishing dimensions, sometimes reaching hundreds of thousands of kilometers across, an ethereal halo that can even surpass the size of giant planets like Jupiter. This expansive, shimmering cloud gently expands as the comet's icy core slowly releases its frozen vapors, creating a temporary radiant atmosphere around its solid heart. The coma is a fleeting, majestic display, a testament to the comet's gradual sublimation under the Sun's warming influence, a soft glow in the cosmic darkness. As comets repeatedly journey through the inner solar system, they gradually lose their volatile materials with each close pass by the Sun. Over many such celestial circuits, they can eventually deplete most of their ice, transforming into what astronomers refer to as extinct comets. These silent wanderers have completed their fiery, luminous displays, their volatile essences having gently sublimated away. What remains is often a dark, rocky core that closely resembles an asteroid, continuing its long, patient orbit through the solar system, a quiet testament to a past filled with brilliant ethereal light. They are the tranquil echoes of former cosmic spectacles, now drifting in peaceful solitude, their vibrant tales a distant memory. As we continue our gentle exploration, our gaze turns to the vast and tranquil region known as the main asteroid belt. This expansive celestial thoroughfare is gracefully situated between the orbits of the tranquil red planet Mars and the colossal gas giant Jupiter. It is home to millions of asteroids, each larger than 1 kilometer across, quietly orbiting our Sun. This vast region is not a chaotic jumble, but rather a gentle cosmic debris field, a serene collection of countless rocky bodies, each following its measured path in a grand, unhurried cosmic dance. The sheer number of these ancient fragments speaks to the early, formative years of our solar system, a time when material was still gathering and shaping before settling into its current, more placid configuration. Despite its descriptive name, the asteroid belt is, perhaps surprisingly, mostly empty space. The individual objects within it are spread out over truly vast distances, making collisions between them relatively rare occurrences. A spacecraft navigating this immense region would not encounter a dense, hazardous obstacle course, but would instead find itself drifting through an expansive, serene void, with distant asteroids appearing as mere specks of light against the profound darkness. This peaceful emptiness allows for safe passage, a testament to the efficient spacing of cosmic objects, ensuring a calm journey through this ancient realm. Comets, unlike the more circular paths of many asteroids, typically follow highly elliptical orbits. These long, graceful arcs bring them close to the Sun for only a brief period, where they awaken and display their luminous tails before sending them back into the distant, cold reaches of the solar system. Here, far beyond the known planets, they slumber in profound stillness, their icy cores preserved in the deep freeze of interstellar space for vast stretches of cosmic time. Their journeys are a patient ballet, a slow, deliberate swing from the inner warmth to the outer chill, a true testament to the immense scale of our Sun's gravitational embrace. Among these icy travellers, we distinguish between two main categories based on their orbital periods. Short-period comets, as their name suggests, complete an orbit around the Sun in less than 200 years. These more frequent celestial visitors often originate from the Kuiper belt, the disc-shaped region beyond Neptune. Their predictable returns provide regular and gentle celestial displays, appearing in our skies at measured intervals, offering astronomers consistent opportunities for study and observation. They are like familiar friends, gracefully returning to our cosmic neighbourhood with serene regularity. In contrast, long-period comets embark on much grander, more extended journeys. These ancient messengers can take to complete a single orbit around the Sun. They originate from the much more distant Oort cloud, the vast, spherical shell that surrounds our entire solar system. These pristine objects arrive from the outermost fringes of our cosmic domain, offering invaluable glimpses of material that has remained largely untouched and unaltered for eons, preserving the very earliest conditions of our solar system's birth. Their infrequent appearances are a profound reminder of the immense scale of cosmic time and distance. Beyond the main belt, some asteroids share a unique orbital relationship with larger planets. These are known as Trojan asteroids, and they gracefully share an orbit with a larger planet, clustering around stable gravitational points called Lagrangian points. A prime example is the thousands of Trojans that peacefully orbit Jupiter, leading and trailing the gas giant in its vast celestial path. These cosmic companions follow a stately procession, gravitationally tethered to their colossal neighbour, maintaining a delicate balance within the solar system's intricate orbital mechanics. Their existence is a beautiful demonstration of gravitational stability over cosmic timescales. Our own planet is not immune to the gentle, yet persistent proximity of these celestial wanderers. Near-Earth objects, or NEOs, encompass both asteroids and comets, whose orbits bring them within 30 million miles of Earth's own orbital path. These celestial neighbours, though generally passing at safe distances, require careful and continuous monitoring by astronomers. This vigilant tracking ensures their gentle passage through our cosmic vicinity, allowing us to anticipate any potential close approaches and to better understand the dynamic interactions within our immediate solar neighbourhood. It is a quiet, ongoing watch over our planet's cosmic safety. Finally, the paths of these smaller celestial bodies are not always perfectly stable. They can be subtly influenced by a phenomenon known as the Yarkovsky effect. This delicate, non-gravitational force arises from the gentle emission of thermal radiation from the asteroid's unevenly heated surface. Over long periods, this subtle push can gradually alter the orbits of small asteroids, gently nudging them from their predictable paths. This delicate effect subtly reshapes their cosmic journeys, a quiet testament to the intricate interplay of heat, light, and motion in the vastness of space. It reminds us that even the smallest forces can have profound, long-term consequences in the patient unfolding of cosmic trajectories. As we continue our tranquil journey through the solar system, we observe how fundamental conditions shape the very nature of these celestial bodies. The formation of the solar system's snow line, often referred to as the frost line, played a pivotal role in determining whether icy comets or rocky asteroids would take shape at a given distance from the Sun. This invisible boundary delineated the regions where water ice and other volatile compounds could condense from gas into solid form. Closer to the Sun, where temperatures were higher, only rocky and metallic materials could coalesce, forming asteroids. Beyond this gentle line, however, the colder temperatures allowed ice to persist, paving the way for the formation of icy comets and outer solar system bodies. This fundamental distinction shaped the very composition of celestial bodies, creating a serene division in our cosmic neighbourhood between the dry, rocky inner realms and the icy, volatile outer reaches. It is a quiet testament to the thermal gradient of the early solar nebula, a subtle yet profound influence on the architecture of our planetary system. Despite the vast number of objects in the main asteroid belt, it is a fascinating fact that the total mass of all these asteroids combined is less than that of Earth's own moon. Even with millions of individual objects from tiny pebbles to the dwarf planet Ceres, this vast collection of remnants represents only a fraction of the material that might have formed a single, larger planet. This gentle realization underscores the immense scale of the early solar system's formation processes and Jupiter's powerful gravitational influence, which prevented these building blocks from fully coalescing into a grander world. Instead, they remain a scattered, peaceful collection, a quiet testament to a planet that never quite formed, drifting in harmonious orbits around our Sun, each a small piece of unfulfilled cosmic destiny. Comets, in their graceful journeys through the inner solar system, undergo a gradual transformation. Each time they pass close to the Sun, their icy cores are gently warmed, causing their volatile materials to sublimate and stream away into space. This means that comets gradually lose material with every close solar encounter, eventually diminishing in size over many orbits. Their icy hearts slowly release their ancient contents, leaving a delicate trail of dust and gas that subtly enriches the inner solar system with pristine, ancient particles. This process is a slow, patient erosion, a serene shedding of material that sculpts the comet's form and eventually leads to its quiet fading from a luminous display to a dormant rocky core. It is a beautiful illustration of cosmic impermanence, a celestial body slowly returning its essence to the wider cosmos. These dispersed trails of cometry, and, more rarely, asteroidal debris give rise to one of the most enchanting celestial phenomena: meteor showers. These occur when Earth, in its own gentle orbit, passes through these streams of particles left behind by its cosmic neighbours. As these tiny cosmic fragments gracefully enter our planet's atmosphere, they burn up due to friction, creating a gentle, sparkling display of light in the night sky. These shooting stars are a tranquil reminder of the constant, subtle interaction between our planet and the vast, particulate matter of the solar system, a luminous dance of tiny cosmic visitors meeting their end in a serene atmospheric glow. Each streak of light is a fleeting whisper from a distant comet or asteroid, a beautiful, ephemeral moment in our atmosphere. The internal structure of many asteroids is another area of quiet wonder. Instead of being solid, monolithic chunks of rock, many asteroids are actually rubble piles, loosely bound collections of smaller rocks and dust held together by their own gentle gravity. These porous structures suggest a long and intricate history of gentle collisions, fragmentation, and subsequent reaccumulation, forming a delicate cosmic mosaic. Imagine a loose assemblage of celestial building blocks, patiently drawn together over eons into a cohesive yet internally fractured entity. This rubble pile nature has significant implications for understanding how these bodies might behave if ever gently nudged or interacted with, revealing a surprising softness beneath their seemingly rigid exteriors. While most cosmic encounters are distant and benign, Earth occasionally experiences more direct interactions. The Chelyabinsk meteor event in 2013 served as a powerful, yet non-dramatic demonstration of the potential impact risk from even relatively small objects entering Earth's atmosphere. This large asteroid, upon its entry, created a bright flash and a significant shockwave, causing widespread but thankfully non-fatal damage across a region in Russia. This natural spectacle, while notable, was a serene reminder of the dynamic interplay between our planet and its cosmic neighbourhood, underscoring the importance of ongoing celestial surveillance. It was a gentle, luminous visitation, a quiet testament to the ever-present cosmic ballet. A more profound example of such an atmospheric event is the Tunguska event of 1908. This massive airburst, which occurred over a remote forested area in Siberia, is widely believed to have been caused by a comet or asteroid that exploded high in the atmosphere before it ever touched the ground. This unseen celestial visitor released energy equivalent to many tons of TNT, gently flattening millions of trees over a vast area, yet leaving no impact crater. The absence of a crater further supports the idea of an atmospheric explosion, a silent, powerful transformation of cosmic energy into atmospheric shockwaves, leaving behind a profound natural scar on the landscape without a direct terrestrial impact. It was a subtle, yet immensely powerful cosmic event, a quiet force reshaping a remote forest. In response to the ever-present, though subtle, possibility of future celestial encounters, humanity has begun to develop gentle strategies for planetary defense. The DART mission, or Double Asteroid Redirection Test, successfully demonstrated such a technique by subtly altering the orbit of an asteroid moonlet. This gentle nudge, achieved by intentionally colliding a spacecraft with the small asteroid Dimorphos, showcased humanity's growing ability to subtly influence the paths of distant celestial bodies. It was a quiet yet profound step towards safeguarding our planet, demonstrating that with careful observation and precise action, we can gently guide the cosmic dance of these ancient wanderers, ensuring a serene future for Earth within its dynamic solar system. This mission marked a calm, confident stride into a new era of cosmic stewardship. As we continue our tranquil journey, let us gently clarify the subtle distinctions between the smaller fragments that grace our solar system. A meteoroid is a small piece of an asteroid or a comet, typically measuring less than 1 meter across. These tiny fragments drift silently through the vast emptiness of space, often unseen and unheralded. They are the quiet precursors to the luminous streaks of light that we sometimes observe gracefully arcing across our night sky, small, unassuming travelers on their long cosmic paths, patiently awaiting their fiery entrance into an atmosphere. Each one is a silent witness to the solar system's ancient history, a minuscule piece of rock or ice traveling through the void. When one of these meteoroids eventually encounters Earth's atmosphere, it undergoes a beautiful, fleeting transformation. A meteor is the streak of light we see as a meteoroid enters our planet's protective atmospheric layers and gently burns up due to friction. Commonly known as a shooting star, this ephemeral celestial display is a gentle reminder of the constant cosmic dust that gracefully showers our planet. It is a luminous farewell, as the tiny cosmic fragment transforms into a brief radiant glow before dispersing into the atmospheric currents, a serene, twinkling moment in the vastness of the night. Should any part of a meteoroid survive its fiery journey through the atmosphere and gently land on Earth's surface, it is then called a meteorite. These precious cosmic stones offer tangible links to the ancient solar system, often collected and meticulously studied by scientists. Each meteorite is a silent messenger, carrying invaluable information about the conditions, compositions, and processes that shaped our cosmic neighborhood billions of years ago. They are physical pieces of the universe, patiently waiting to reveal their secrets through careful scientific observation, offering a profound, tactile connection to the cosmos. The distinction between a comet and an asteroid, while generally clear, can sometimes be surprisingly subtle. This is especially true for certain objects found in the outer solar system, which may outwardly appear rocky, but contain significant amounts of ice beneath their surfaces. These transitional objects gracefully challenge our rigid classifications, revealing the fluid and interconnected nature of cosmic evolution. They remind us that the universe is not always neatly categorized, but rather a spectrum of possibilities, where rocky and icy compositions can subtly merge, blurring the lines and offering new insights into the diverse origins of celestial bodies. Interestingly, comets are often inherently very dark, reflecting only a small percentage of the sunlight that falls upon them. This low reflectivity makes them particularly difficult to spot against the profound darkness of space until they draw close enough to the sun to develop their characteristic bright coma and luminous tail. Their dusty, carbon-rich surfaces absorb much of the sun's gentle light, effectively keeping them hidden in the cosmic shadows for most of their long, elliptical journeys. This quiet stealth allows them to remain largely undetected until their icy hearts are awakened by solar warmth, revealing their hidden brilliance. The surfaces of many asteroids, especially the larger ones, are covered in a layer of loose, fragmented rock and dust known as regolith. This fine, powdery blanket is quite similar in texture and composition to the lunar soil found on Earth's moon. This regolith is a testament to billions of years of gentle cosmic bombardment from smaller meteoroids and the subtle processes of surface weathering. It represents a slow, patient accumulation of cosmic debris, creating a soft, textured surface that records the long history of celestial impacts and quiet erosion, a delicate cosmic tapestry woven from countless tiny fragments. Within the bustling main asteroid belt, there are intriguing regions known as the Kirkwood Gaps. These are specific zones where surprisingly few asteroids are found, creating noticeable voids in the distribution of these rocky bodies. These gaps are caused by the powerful yet subtle gravitational influence of Jupiter, which creates orbital resonances with asteroids that attempt to occupy these particular paths. These gravitational nudges gently clear out certain orbital trajectories over long periods, creating quiet, empty zones in the otherwise teeming belt. They are a beautiful illustration of how a distant giant planet can subtly sculpt the distribution of smaller objects through its pervasive gravitational embrace. Among the many meteorites that have graced our planet, the Allende meteorite stands as a particularly famous example. This carbonaceous chondrite provided scientists with some of the oldest and most chemically primitive material ever discovered in the solar system. Its pristine structure, largely unaltered since the birth of our Sun, offers a profound glimpse into the initial conditions and chemical makeup from which our entire planetary system gently arose. Studying its delicate inclusions and ancient minerals allows scientists to piece together the very first moments of cosmic creation, a tangible record of the primordial soup that birthed worlds. The age of meteorites can be precisely measured using a technique called radiometric dating. This scientific method allows researchers to determine how long ago the meteorite's constituent elements solidified, providing key and accurate information about the age of the solar system itself. These ancient rocks serve as cosmic clocks, silently recording the passage of nearly 4.6 billion years, offering invaluable benchmarks for understanding the timeline of cosmic evolution. Each dated meteorite is a quiet confirmation of our solar system's venerable age, a precise timestamp from the distant past. Finally, many meteorites, particularly those rich in iron, exhibit subtle yet fascinating magnetic properties due to their metallic composition. These gentle magnetic signatures offer valuable clues about the presence and strength of magnetic fields in the early solar system, as well as the intricate cooling processes of their parent bodies. By studying these ancient magnetic imprints, scientists can reconstruct the conditions under which these celestial fragments formed and evolved, providing a deeper understanding of the magnetic environments that prevailed in our cosmic infancy. These subtle forces reveal a hidden aspect of cosmic history, a quiet magnetism woven into the fabric of ancient rock. Our journey through the delicate interplay of cosmic elements now leads us to consider the ethereal beauty of cometary tales and the pervasive unseen forces that patiently sculpt their luminous forms. The solar wind, a continuous and subtle stream of charged particles emanating from the Sun, is fundamentally responsible for shaping the ion tails of comets. This gentle, pervasive celestial breeze, composed primarily of protons and electrons flowing outward from our star at immense speeds, consistently pushes the ionized gases of the comet's coma outward, directly away from the Sun's radiant embrace. This constant interaction meticulously sculpts the delicate blue luminescence into its characteristic straight, radiant form, an almost transparent ribbon of light stretching across the vastness of space. This continuous flow gently guides the ethereal path of the ion tail, creating a dynamic diagram of the Sun's constant outflow of energy and its profound yet silent influence across the expansive solar system. It is a powerful, yet non-dramatic force that gracefully defines these luminous wanderers, painting a serene, ever-changing masterpiece against the dark canvas of the cosmos, a true testament to solar interaction. Among these celestial spectacles, Comet Halley stands as perhaps the most renowned and universally celebrated short-period comet. Its predictable return, gracing Earth's skies every 75 to 76 years with serene regularity, has captivated observers for countless millennia, weaving its luminous presence into the rich tapestry of human history, art, and folklore across diverse cultures around the globe. This reliable periodic visitation is a serene celestial dance, a familiar and eagerly anticipated visitor in our night sky, its luminous arc a gentle reminder of the enduring rhythmic cycles of the cosmos. Each appearance offers a tranquil opportunity to witness an ancient traveller, a testament to the unchanging, elegant laws governing our solar system's delicate mechanics. From ancient Babylonian records to modern telescopic observations, Comet Halley's graceful passage has been a consistent calming presence, a celestial clock marking the patient passage of generations with its quiet, luminous return. Its long, measured orbit ensures its gradual appearance, a patient cosmic beacon. Our scientific curiosity has also led humanity to dispatch remarkable robotic emissaries to these icy realms, extending our gentle reach far beyond Earth's comfortable confines. The Stardust mission, for example, successfully undertook the extraordinary feat of meticulously collecting dust samples directly from Comet Wild 2 in 2004. This pioneering spacecraft gracefully navigated through the comet's expansive coma, carefully capturing microscopic particles of cometary material in a specialized aerogel collector designed to slow them down without damage. These precious microscopic particles were then carefully returned to Earth for meticulous analysis in specialized pristine laboratories. These minute samples offered direct and invaluable evidence of the comet's pristine, unaltered composition, material that had remained largely untouched and perfectly preserved in the deep freeze of space since the very dawn. As we gently drift through the solar system's ancient history, a key question arises. Why did the material in the asteroid belt never coalesce into a single, grand planet? The scientific consensus points to the immense gravitational influence of Jupiter as the primary factor. The colossal planet's powerful yet subtle pull gently stirred the region, preventing the smaller bodies from gathering together into a cohesive world. Instead of allowing for the tranquil accretion of a new planet, Jupiter's pervasive gravity maintained a scattered collection of smaller bodies, ensuring that the asteroid belt remained a realm of unformed remnants rather than a grand new celestial sphere. This colossal planet acted as a silent shepherd, subtly shaping the destiny of an entire planetary region, orchestrating a cosmic ballet of countless small objects. Our understanding of comets was significantly advanced by the dirty snowball model, elegantly proposed by astronomer Fred Whipple. This simple, yet profound description accurately characterizes their composition as primarily a mixture of ice, dust, and rock. This model helps us to beautifully understand how these icy bodies gracefully interact with solar radiation as they approach the Sun, explaining the serene sublimation of their volatile components and the subsequent formation of their luminous comae and tails. It is a testament to the clarity that can emerge from elegant scientific thought, providing a tranquil framework for comprehending these ethereal visitors. Many of the asteroids we observe today are not primordial, intact bodies, but rather are thought to be fragments of larger protoplanets. These ancient, nascent worlds were broken apart by gentle yet persistent collisions in the chaotic early solar system. Their fractured forms are a silent testament to the slow, patient processes of cosmic evolution, where celestial bodies underwent periods of both formation and gentle disintegration. These remnants, now drifting in their orbits, carry the echoes of larger, unfulfilled planetary aspirations, their diverse shapes and compositions reflecting a long history of cosmic reshaping. Even with millions of individual objects, the entire asteroid belt contains a surprisingly modest amount of material. If all the asteroids within the main asteroid belt were somehow combined into a single body, they would form a celestial sphere far smaller than Earth. This vast collection of minor planets represents a quiet, unformed realm in our cosmic neighborhood, a gentle reminder that while space is immense, the distribution of matter can be quite sparse. It is a testament to the scale of planetary formation, where vast amounts of material are required to build even a modest world. Comets, in their active phases, can sometimes surprise us with sudden bursts of activity. These outbursts are characterized by dramatic yet gentle increases in their brightness, caused by a rapid and unexpected release of gas and dust from their nuclei. This phenomenon might occur due to the exposure of a fresh patch of highly volatile ice, perhaps uncovered by a minor impact or a subtle thermal crack, allowing for a sudden surge of sublimation. These luminous events are a fleeting display of a comet's hidden activity, a transient moment of increased radiance in its long, silent journey, offering astronomers a dynamic glimpse into their internal processes. For the vast majority of their existence, while far from the Sun, a comet's nucleus remains in a state of profound stillness and intense cold. The average temperature of a comet's nucleus in these distant, frigid reaches of the solar system is extremely low, often plummeting below -200 degrees Celsius. These intensely cold conditions are crucial for preserving its icy components, ensuring that the delicate mixture of water ice, frozen gases, and dust remains stable for eons. In these frigid depths, ancient volatiles remain in a state of profound stillness, untouched by solar warmth, patiently preserving the pristine building blocks of the early solar system, a true cosmic deep freeze. The term asteroid itself carries a gentle historical echo. It literally means star-like, a name coined by early astronomers because, when viewed through their telescopes, these celestial bodies appeared as mere points of light, much like distant stars. This was in distinct contrast to the disk-like resolved appearance of planets. This gentle naming reflects their distant twinkling presence in the night sky, their true nature as small, rocky worlds only revealed with more advanced observational techniques. It is a testament to the subtle beauty and mystery that these seemingly star-like objects held for early stargazers. Their volatile ice and gases are gradually depleted. Over eons, some comets lose all their active materials, transforming into extinct comets. These former icy travelers now drift silently through space, their luminous past a fading memory, leaving behind a rocky, inert core. These objects, having completed their grand luminous displays, now resemble asteroids in their composition and behavior, becoming quiet, rocky wanderers, their vibrant tails a distant memory, continuing their long, patient orbits as silent witnesses to cosmic time. Adding to the complexity of our understanding, the presence of water ice has been detected on some asteroids, particularly those residing in the colder outer regions of the asteroid belt. These intriguing discoveries gently blur the traditional distinction between rocky asteroids and icy comets, suggesting a more diverse and interconnected composition among these minor bodies than previously understood. These icy asteroids hint at a rich, varied history of material distribution within the solar system, where ice was not solely confined to the distant realms of comets, but also preserved within some rocky fragments, offering new insights into the subtle chemistry of the early solar system. A truly unique cosmic spectacle unfolded in 1994 with the Shoemaker-Levy 9 comet. This celestial visitor, due to Jupiter's immense gravitational embrace, was gently pulled apart into 21 distinct fragments, creating a string of luminous pearls in space. These fragments then embarked on a series of soft, spectacular impacts with the giant planet Jupiter. This sequence of gentle impacts left temporary dark scars on Jupiter's majestic atmosphere, a profound and visible testament to the immense gravitational power of the solar system's largest planet. It was a rare and beautiful demonstration of celestial mechanics, a cosmic dance of fragmentation and absorption, observed with quiet wonder by astronomers across our solar system. Our understanding of the solar system's ancient past is subtly enriched by the gentle whispers found within meteorites. Among these precious cosmic stones, carbonaceous chondrite meteorites reveal a profound secret, offering a unique window into the universe's earliest epochs. These types of stony meteorites often contain tiny, microscopic presolar grains, exquisite particles that demonstrably predate our Sun and the entirety of our solar system itself. These minuscule specks are truly ancient messengers, carrying pristine material from distant stars that lived and died long, long ago, their stardust now gently incorporated into the fabric of our own cosmic neighborhood. They offer an unparalleled, tranquil glimpse into the universe's history even before our Sun began its luminous reign, a quiet connection to other stellar nurseries and the intricate chemical processes that unfolded across the vastness of space eons before our planet took shape. Each grain is a testament to the grand cosmic recycling of matter, a silent fragment of a stellar past, patiently awaiting discovery and interpretation. Returning our gaze to the luminous travelers that grace our skies, the sheer scale of cometary tales is a source of continuous wonder and serene admiration. These ethereal streamers, born from the sun's gentle warmth and the comet's icy core, can stretch for millions of kilometers across the profound darkness of space, unfurling with an unhurried grace. Their immense size allows them to create a magnificent, sweeping display that can sometimes be seen without the aid of a telescope, a breathtaking spectacle painted across the night sky for patient observers. These luminous extensions gently unfurl across the vastness of space, a radiant brushstroke in the cosmic canvas, forming a temporary shimmering bridge between the comet's icy heart and the boundless void. The graceful arc and radiant glow are a tranquil reminder of the subtle forces at play, shaping beauty from ice and dust, visible even to the unaided, patient eye, a silent testament to solar interaction. Within the bustling yet serene main asteroid belt, we encounter a diverse array of rocky worlds, each charting its own unique course. Pallas, distinguished as the third largest asteroid in this vast region, stands out not just for its considerable size, but also for its highly inclined orbit. This unusual, almost jaunty path takes it significantly out of the main plane where most other asteroids reside, making it a particularly challenging target for spacecraft missions, requiring intricate orbital maneuvers to reach. Its unique trajectory adds a subtle complexity to the celestial ballet of the asteroid belt, a graceful deviation from the more common orbital planes of its neighbours. This distinctive inclination offers delicate clues about the early, dynamic interactions within the solar system, perhaps hinting at ancient gravitational nudges that set Pallas on its singular, elegant course, preserving its unique celestial dance through the eons. The surfaces of many celestial bodies within our solar system bear silent witness to eons of cosmic encounters. The meticulous study of impact craters on planetary surfaces, such as the ancient pockmarked face of our Moon and the dust-swept plains of Mars, provides invaluable insights into the long and intricate history of asteroid and comet bombardments. These gentle depressions, ranging from vast circular basins to tiny subtle pockmarks, are effectively silent archives of countless cosmic encounters, each etched into the ancient landscapes with unhurried precision. They patiently record the subtle yet persistent rain of debris that has sculpted these worlds over billions of years, offering a tranquil chronology of past celestial interactions and the slow, patient evolution of planetary surfaces, a quiet geological diary meticulously written in stone by the cosmos itself. Revisiting their profound cosmic significance, comets are widely believed to have played a crucial, gentle role in the early development of Earth. They are thought to have been quiet couriers, patiently delivering substantial quantities of organic compounds and water to our nascent planet billions of years ago. These delicate ingredients were absolutely crucial for the emergence of life, providing the fundamental building blocks and the essential solvent necessary for complex biological processes to gently begin and flourish. These celestial travellers, through their ancient icy deliveries, help to weave the delicate threads of our planet's biological tapestry, making them silent, essential contributors to the very existence of life as we know it, a profound connection between the distant cosmos and our vibrant living world, a truly gentle seeding of life. The colossal gravitational pull of Jupiter continues to exert a significant and far-reaching influence on the orbits and overall population of asteroids within our solar system. This immense planet acts as a gentle shepherd, subtly shaping the asteroid population in various ways over vast stretches of time. Its powerful gravity can sometimes gently eject asteroids from the main belt, sending them on new, distant trajectories into the outer solar system, or it can draw them into new, stable orbital paths, such as the balanced Trojan points. This colossal planet's pervasive influence orchestrates a continuous, subtle reshaping of the asteroid population, guiding their movements and distribution through its immense gravitational embrace, a silent, powerful force in the cosmic dynamics of our planetary system, ensuring a delicate and enduring balance. One of the most captivating aspects of a comet's ion tail is its distinct bluish hue, a serene and luminous stream of light that mesmerizes observers. This ethereal glow is produced through a beautiful process known as fluorescence, caused by the intricate interaction of cometary ions with the solar wind. As the charged particles from the sun gently collide with and excite the gases in the ion tail, these gases absorb energy and then re-emit it as light, creating a serene, luminous stream that stretches across space. This delicate dance of light and charged particles visually represents the continuous flow of energy from our star, a vibrant, yet tranquil demonstration of cosmic physics, a subtle interplay that paints the ion tail in its characteristic mesmerizing blue, a fleeting, elegant natural phenomenon. Our collective understanding of these quiet cosmic wanderers, the comets, owes a considerable debt to the patient dedication of amateur astronomers. These diligent sky watchers, with their keen eyes and persistent observations, patiently scan the night sky for new celestial visitors, often making the initial discoveries of previously unknown comets before professional observatories. Their dedicated observations significantly contribute to our collective understanding of these elusive bodies, adding new data points to our growing catalogue of cosmic travellers. This quiet, global network of stargazers exemplifies the enduring human curiosity about the cosmos, a collaborative effort that gently expands our knowledge of the universe, revealing new wonders with each passing night, a serene and shared pursuit of cosmic truth. To maintain clarity in our cosmic lexicon, it is helpful to reiterate the precise definition of a meteoroid. The term meteoroid refers specifically to the object itself, while it is still drifting silently in the vast emptiness of space before it encounters any planetary atmosphere. This distinction highlights its solitary journey through the profound stillness of the cosmos, emphasizing its identity as an independent small piece of cosmic history adrift in the void. It is a silent traveller, a potential shooting star or a future meteorite, patiently awaiting its next celestial interaction, a tiny fragment of the universe's grand narrative, a quiet celestial pebble on an endless cosmic road. Finally, the dirty snowball model of comets, a cornerstone of cometary science, further suggests that within their icy nuclei, there exist numerous tiny pockets of trapped gases. When these icy bodies are gently warmed by the sun during their approach through the inner solar system, these trapped gases begin to sublimate, expanding and slowly escaping from the nucleus. This gradual, controlled release of material creates the ethereal glow that defines a comet, forming its luminous coma and magnificent tails. It is a serene and continuous process, a slow unveiling of ancient volatiles that transforms a dark, icy lump into a brilliant, ephemeral beacon, a testament to the subtle power of solar warmth. The gentle exhalation of these frozen compounds creates the very essence of a comet's radiant beauty, a quiet cosmic marvel. As we continue our tranquil exploration of celestial objects, we turn our attention to the silent arrivals that occasionally grace our planet. The vast majority of meteorites discovered on Earth are classified as stony meteorites. These fascinating cosmic stones often resemble terrestrial rocks, yet upon closer examination, they reveal unique compositions and internal structures that set them apart. These silent arrivals offer tangible and profound connections to the ancient, unformed material of our solar system, providing direct samples of the primordial matter from which planets, including our own, eventually coalesced. They are like gentle whispers from the past, each fragment holding a unique story of cosmic origins, patiently awaiting scientific interpretation. Their presence on Earth's surface is a testament to the continuous subtle exchange of matter across the solar system, a quiet rain of ancient cosmic debris. Comets, while known for their luminous displays, can also undergo more dramatic transformations as they draw close to the Sun. Some comets can gently break apart into multiple pieces, a process of subtle fragmentation caused by the combined effects of intense solar heating and the delicate tidal forces exerted by the Sun's gravity. This quiet disintegration creates a scattered trail of smaller, yet still luminous fragments, each continuing its own brief radiant journey. This celestial unravelling is a testament to the gentle, yet persistent forces that shape these icy wanderers, revealing the fragile nature of their nuclei as they encounter the warmth and gravitational embrace of our star, a serene, slow process of cosmic dissolution. Within the asteroid belt, the celestial body Vesta stands out not only for its brightness, but also for its considerable size. It is the largest known asteroid, with an impressive diameter of roughly 530 kilometers, making it substantial enough to be considered a protoplanet. Its considerable size and evidence of a differentiated interior, meaning it has distinct layers like a core, mantle, and crust, suggest a complex early history, hinting that it began to form into a miniature world in its own right before its growth was halted. Vesta offers a profound glimpse into the internal processes of larger celestial bodies, a quiet, ancient world that never quite reached full planetary status, but holds the secrets of such aspirations within its rocky heart. The meticulous study of meteorites provides scientists with an invaluable window into the fundamental composition of the early solar system. By analysing the elements, minerals, and isotopic ratios within these cosmic samples, researchers can discern the precise chemical ingredients that were available for planet formation billions of years ago. These cosmic samples are like gentle whispers from the past, revealing ancient chemical recipes and the pristine conditions that prevailed during the birth of our planetary system. Each meteorite is a silent, tangible archive, holding the delicate secrets of cosmic chemistry and the foundational materials that ultimately gave rise to stars, planets, and perhaps even life itself, a profound connection to our cosmic heritage. Beyond the individual objects, the subtle presence of cosmic dust permeates our solar system. The zodiacal light, a faint ethereal glow that can sometimes be observed along the ecliptic plane after sunset or before sunrise, is a beautiful manifestation of this cosmic dust. This subtle luminosity is caused by sunlight gently scattering off microscopic particles of cosmic dust, much of which originates from the ongoing activity of comets and the slow collisions within the asteroid belt. It is a pervasive, quiet light that serves as a gentle reminder of the scattered cosmic debris that subtly fills the space between the planets, a serene, diffuse glow that paints the inner solar system with a delicate, almost imperceptible radiance, a testament to the constant, gentle shedding of material from ancient celestial wanderers. The Kuiper Belt, residing in the distant tranquil reaches beyond Neptune, is a region of immense cosmic significance. It is much wider and considerably more massive than the main asteroid belt, harbouring a vastly greater number of icy objects. This distant, tranquil region is a vast repository of primordial ice, silently orbiting at the solar system's cold, outer edge, preserving material largely unchanged since the earliest epochs. Its immense size and rich population of icy bodies make it a crucial area for understanding the origins of short-period comets and the early architecture of our planetary system. It is a realm of profound stillness, where countless icy worlds drift in serene solitude, a quiet treasury of cosmic history. Looking beyond our solar system, we find cosmic nurseries where the processes of celestial formation are still unfolding. The pillars of creation, majestic structures within the Eagle Nebula, are iconic regions of intense star formation. Here, vast clouds of cosmic dust and gas gently coalesce under gravity, a process remarkably similar to how asteroids and comets first formed in our own solar system. These cosmic nurseries are where new celestial bodies gently take shape, where the raw materials of the universe slowly gather and ignite, creating new stars and their accompanying planetary systems. They are vibrant, yet serene, testament to the ongoing cycle of cosmic creation, mirroring the ancient processes that gave birth to our own world, a continuous, gentle unfolding of stellar and planetary genesis. The presence of water and organic molecules on comets and asteroids carries profound implications for the future of space exploration. These ancient materials suggest that these celestial bodies could serve as invaluable targets for future resource extraction, offering gentle sustenance for humanity's expanding presence beyond Earth. Water, in particular, could be harvested for drinking, for growing food, or for conversion into rocket fuel, providing essential resources that could enable long-duration missions and the establishment of permanent outposts. Their ancient materials might offer gentle sustenance for future space exploration, turning these cosmic wanderers into vital waypoints for humanity's serene journey into the stars, a quiet promise of cosmic abundance. On Earth, the subtle, enduring marks of past cosmic visitors are etched into our planet's very surface. The gentle impact of a meteorite can create unique geological features, most notably impact craters. These circular depressions, formed by the sudden collision of a celestial body, slowly erode and change over millions of years due to geological processes like weathering and tectonic activity. These quiet depressions are subtle scars on the Earth's ancient face, serving as tangible evidence of ancient cosmic visitors and the dynamic history of our planet's interactions with its celestial neighbourhood. Each crater is a silent testament to a moment of cosmic encounter, a geological memory of an ancient, gentle impact. Ultimately, the comprehensive study of comets and asteroids offers a profound and holistic understanding of the conditions that ultimately led to the formation of Earth and other planets in our solar system. These ancient remnants, whether icy or rocky, are truly gentle storytellers, recounting the serene origins of our home world and its celestial companions. By analysing their compositions, orbits and structures, scientists can piece together the intricate puzzle of planetary genesis, revealing how the raw materials of the early solar nebula slowly coalesced and evolved into the diverse array of planets we see today. They provide a tranquil narrative of creation, a gentle unfolding of cosmic events that ultimately led to the emergence of our vibrant living planet, a quiet epic of cosmic birth. Our understanding of these intricate celestial mechanics continues to deepen as we observe the subtle forces at play. The orbital paths of asteroids, for instance, are often delicately influenced by gravitational resonances with Jupiter. These occur when an asteroid's orbital period around the Sun forms a simple, harmonious fraction, such as 1/2 or 1/3 of Jupiter's much longer orbital period. These gravitational harmonies create subtle, yet profound patterns in the asteroid belt's population, sometimes gently clearing out specific orbital regions to form the well-known Kirkwood gaps, or conversely, stabilizing other paths into distinct families of asteroids. This intricate interplay beautifully demonstrates how the immense gravitational presence of the gas giant gently, yet persistently, sculpts the distribution of countless smaller bodies, orchestrating a complex, unhurried cosmic ballet that maintains a delicate balance within the vast expanse of the main asteroid belt. It is a testament to the pervasive, subtle influence of cosmic forces shaping celestial movements over eons, creating zones of quiet stillness and harmonious motion, a rhythmic, gravitational dance. In the formative years of our solar system, an invisible yet crucial boundary emerged, defining the fundamental chemical makeup of developing celestial bodies. This boundary is known as the snow line or frost line. This gentle transition marked the specific distance from the Sun where volatile compounds, particularly water ice, could condense from a gaseous state into solid form and persist without immediately sublimating due to solar heat. Closer to our nascent star, the intense temperatures kept these volatiles gaseous, allowing only rocky and metallic materials to coalesce into the inner planets and most asteroids. Beyond this serene dividing line, however, the much colder temperatures enabled water ice and other frozen gases to condense, defining the fundamental chemical distinction between the inner rocky planets and the outer icy worlds and comets. This subtle thermal gradient, therefore, profoundly shaped the initial composition of all celestial bodies, creating a clear, natural separation that influences their characteristics even to this day, a quiet, formative boundary in the cosmic nursery, dictating the very essence of planetary building blocks. The internal composition of a comet's nucleus can exhibit subtle, yet significant variations, even among objects that appear similar from afar. Some comets may be notably richer in dust with a higher proportion of silicate and carbonaceous particles, while others possess a greater abundance of water ice and other frozen volatile gases like carbon dioxide and methane. These subtle differences in the precise ratio of ice to dust directly influence their activity levels when they gently approach the Sun. A comet with a higher ice content might display a more vigorous and luminous coma and tails, releasing a greater volume of gas and dust, while a dustier nucleus might produce a less effusive yet still graceful display. These individual compositional nuances create a diverse and captivating array of luminous displays as comets gently approach the Sun, each unfolding its unique celestial personality, a testament to the varied conditions and materials from which they originally formed, ensuring that no two cometary encounters are ever precisely alike. A quiet cosmic individuality reflecting their diverse origins. In the realm of planetary defense, scientists have developed a fascinating and precise concept known as a gravitational keyhole. This term describes a minuscule region in space, often no larger than a few hundred meters across, where an asteroid's trajectory could be delicately altered by a subtle gravitational encounter with a planet, such as Earth or Venus. A slight, deliberate nudge at such a keyhole, perhaps from a gentle spacecraft impact, could subtly change an asteroid's path just enough to cause a future Earth impact, or conversely, to steer it safely away from our planet. Understanding these delicate pathways and precise timing allows for the development of potential mitigation strategies, enabling humanity to gently guide the paths of potentially hazardous celestial bodies, ensuring a serene future for our home planet. This foresight represents a calm, calculated approach to cosmic safety, a delicate manipulation of gravitational forces for the protection of Earth, a subtle form of cosmic navigation, a testament to human ingenuity and foresight. Far beyond the familiar planetary orbits and even the distant Kuiper belt, the Oort cloud stretches into the deepest, most profound reaches of space. This vast and distant ethereal spherical shell is considered the outermost boundary of the Sun's gravitational influence, a serene and almost untouched realm of primordial ice, a true frontier of our solar system. This immense cosmic reservoir is believed to hold an estimated billions of icy fragments, each patiently awaiting its cosmic cue, a subtle gravitational perturbation that might send it on a millennia-long journey toward the inner solar system. These fragments are the pristine building blocks of the solar system, perfectly preserved in profound stillness for eons, undisturbed by the inner warmth of our star. The Oort cloud is a quiet, almost mythical place where long-period comets begin their immense journeys, a boundless treasury of ancient volatiles, a testament to the vast, tranquil expanse that surrounds our stellar home, a region of profound, enduring cosmic peace, a silent, icy cradle. The enduring study of comets and asteroids significantly contributes to our understanding of the profound potential for life beyond Earth. Their analyses consistently reveal the presence of complex organic compounds, including amino acids, which are the fundamental building blocks of proteins and consequently life itself. These silent travelers, carrying these delicate biochemical ingredients across the vastness of space, subtly hint at the widespread distribution of life's fundamental components throughout the cosmos. This suggests that the seeds for life may not be unique or exclusive to our planet, but could be ubiquitous, patiently scattered across the universe, awaiting suitable conditions to gently take root and flourish on other worlds. This offers a profound, tranquil perspective on the universal nature of life's origins, a quiet cosmic promise, expanding our sense of wonder about the intricate tapestry of existence across the stars. Some asteroids, particularly those residing in the stable and less perturbed orbits of the main asteroid belt, have been patiently orbiting the Sun for billions of years. These ancient fragments have remained remarkably unchanged since the very formation of our solar system, acting as steadfast geological archives of the cosmic past. They are patient witnesses to cosmic history, drifting in quiet solitude, their surfaces and interiors preserving the pristine conditions and materials of the early solar nebula. Their long, unhurried journeys through space underscore the enduring stability of certain regions within our solar system, providing astronomers with invaluable, untouched samples of primordial matter that have silently recorded the passage of cosmic time, a serene constancy amidst the dynamic evolution of the universe, embodying ancient cosmic patience and offering a direct window into our solar system's genesis. One of the most beautiful and subtle forces at play in a comet's luminous display is solar radiation pressure. This gentle, yet persistent force emanates directly from sunlight itself, subtly pushing tiny dust particles away from the comet's nucleus. Unlike the solar wind, which sculpts the straight bluish ion tail, radiation pressure is primarily responsible for forming the broader, yellowish, and often gracefully curved dust tail. As the comet moves through space, the dust particles are pushed away, but their inertia causes them to lag behind the comet's trajectory, creating a luminous ephemeral arc in space, a delicate glowing stream. This delicate interaction between light and matter is a testament to the subtle power of our Sun, gracefully shaping the comet's radiant form, a quiet, continuous act of cosmic artistry, painting an elegant, transient curve across the stellar backdrop, a transient celestial phenomenon. The term planetoid is sometimes used interchangeably with asteroid to describe smaller celestial bodies that orbit the Sun. This gentle alternative, though less commonly used in formal scientific contexts today, subtly highlights their potential planetary aspirations, acknowledging that they are indeed small, planet-like objects in their own right. While these bodies never fully coalesced into full-fledged planets, perhaps due to Jupiter's gravitational influence or insufficient available material, the term planetoid offers a poetic recognition of their origins as the building blocks of worlds, suggesting a gentle, arrested development in the grand process of planetary formation. It is a subtle linguistic nuance that reminds us of the continuous spectrum of cosmic objects, from tiny dust grains to colossal gas giants, each playing its unique role in the solar system's serene and evolving narrative, a quiet acknowledgement of their intrinsic nature. The ongoing study of impact events, both those that have occurred in the distant past and those that could potentially occur in the future, from comets and asteroids is a crucial and continuous endeavour for planetary safety. This continuous research helps scientists accurately assess the long-term risk of future celestial collisions with Earth. By meticulously tracking near-Earth objects and modelling their precise trajectories with advanced computational tools, astronomers can maintain a quiet yet persistent monitoring of our cosmic neighbourhood. This gentle vigilance ensures proactive awareness and allows for the development of thoughtful strategies to protect our planet. It is a calm, persistent effort to understand and mitigate cosmic threats, ensuring a gentle future for Earth within its dynamic celestial environment. A testament to humanity's careful stewardship of its home, a quiet, enduring commitment to cosmic well-being, a serene watchfulness. Finally, the continuous discovery of new comets and asteroids, often achieved by dedicated amateur and professional astronomers alike, highlights the dynamic and ever-evolving nature of our solar system. Even billions of years after its birth, our cosmic neighbourhood remains a place of subtle activity and ongoing transformation. These ongoing observations reveal a cosmos in constant, subtle motion, with new objects being found, old ones evolving, and gravitational interactions continually reshaping their paths. This gentle, persistent unveiling of new celestial bodies reminds us that the universe is not static, but a living, breathing entity, always revealing new wonders and insights. A serene and endless journey of cosmic discovery, a tranquil unfolding of endless celestial stories, each a quiet affirmation of the universe's boundless complexity. And now, the vastness of the cosmos begins to gently fade behind your thoughts. You have drifted through 100 quiet wonders, from the ancient stardust carried by meteorites to the ethereal beauty of cometary tales, from the subtle gravitational dances of asteroids to the serene, icy realms where comets begin their immense journeys. You have travelled through cosmic nurseries, soared along luminous streams of charged particles, and glimpsed the delicate interplay of forces that shape our solar system. You are part of this cosmic story, not just an observer, but a participant woven into the fabric of stardust and time. The atoms in your body were forged in the fires of ancient stars. The water that sustains you may have travelled across light years on the back of a comet. Everything within you shares a lineage with the universe itself, born from the same primordial matter that now flows through galaxies and drifts in interstellar clouds. Tonight, as you rest, the cosmos continues its quiet unfolding. Stars are forming, light is travelling, and cosmic dances carry on in silent harmony. You're a small, warm presence within this vast, radiant sea, peacefully floating among the stars. Thank you for journeying through the cosmos tonight. I hope you sleep well and dream softly. Good night.
Hello there, and welcome to Cosmos for Sleep. Tonight, we're drifting through the enchanting realm of planetary moons, uncovering their serene secrets and silent wonders. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe. Let your eyes grow heavy. And let's begin. Europa, a moon of Jupiter, holds a vast subsurface ocean, a hidden world of liquid water beneath its icy shell. Scientists believe this ocean could potentially contain more than twice the volume of all of Earth's oceans combined, a staggering amount of water veiled from direct sight. This immense liquid reservoir makes Europa one of the most compelling places in our solar system to search for signs of life beyond our home planet. Its icy shell acts as a protective barrier, shielding the ocean from the harsh radiation of Jupiter. This tranquil, deep ocean, kept liquid by internal warmth, represents a profound possibility in our quest for understanding life beyond Earth. The sheer scale of this watery world is immense, potentially holding more than 2 times the amount of water found in all of Earth's vast oceans combined, a truly staggering volume of liquid veiled from direct sight. Scientists envision a placid, dark expanse beneath the ice, perhaps gently warmed by subtle hydrothermal vents, creating a serene environment where complex chemistry could unfold. The presence of such a significant body of liquid water, shielded and sustained, speaks to the incredible diversity of environments that can exist even in the frigid, distant reaches of our solar system. This quiet, deep sea, far from the sun's direct light, offers a unique, serene laboratory for studying the delicate conditions under which life might emerge and patiently thrive. Moving outward through the calm expanse of space, Saturn's moon Enceladus presents an even more direct hint of a subsurface ocean. From its southern polar region, magnificent plumes of water vapor and tiny ice particles gracefully erupt into the void. These geyser-like emissions offer a direct sample of the moon's interior, confirming the presence of a vast, warm, liquid water ocean beneath its crust. The gentle streams of material, stretching hundreds of miles into the cosmos, are a mesmerizing spectacle, indicating an active, dynamic interior. Researchers have detected organic molecules, salts, and even silica within these plumes, all components that are considered important for the emergence of life. This active venting suggests ongoing geological processes, perhaps driven by patient tidal heating from Saturn, maintaining a potentially habitable zone far from the Sun. The quiet, consistent expulsion of these particles paints a picture of a moon constantly renewing itself, sharing its hidden watery depths with the universe in a beautiful, measured flow. Shifting our focus to another of Saturn's companions, Titan stands out as a truly unique celestial body. It is the only moon in our entire solar system known to possess a dense, substantial atmosphere. Remarkably, this atmospheric blanket is even thicker than Earth's, creating a hazy orange veil that completely obscures its surface from direct optical view. This thick atmosphere, composed primarily of nitrogen with significant amounts of methane, creates a complex meteorological cycle. Imagine a world where methane forms serene clouds, precipitates as gentle rain, flows into meandering rivers, and collects in vast, tranquil lakes and seas across the surface. The presence of such an intricate atmospheric system, complete with weather patterns and surface liquids, makes Titan a world of profound interest. It offers a glimpse into processes that might subtly resemble early Earth, but with a chemistry based on hydrocarbons rather than water. The veiled, unhurried landscape suggests a slow, continuous cycle of evaporation and condensation, patiently shaping its terrain over eons. Returning to the Jovian system, we encounter Ganymede, a moon of truly immense proportions. This majestic satellite holds the distinction of being the largest moon in our solar system. To truly grasp its scale, consider that Ganymede is larger than the planet Mercury and significantly larger than the dwarf planet Pluto. Its sheer size allows it to command a presence that rivals even some planets. This colossal moon could easily be classified as a planet if it orbited the Sun directly. Its vast icy surface stretches across thousands of miles, revealing a complex and ancient geological history. The grandeur of Ganymede underscores the incredible diversity and scale present within the family of planetary moons, reminding us that some satellites are worlds unto themselves, capable of intricate processes and unique characteristics, patiently evolving over cosmic time. Adding to its distinctiveness, Ganymede is also the only moon in our solar system known to possess its own internally generated magnetic field. This invisible shield, similar to Earth's magnetic field, is believed to be created by the slow, fluid motion of liquid iron within its core. The presence of such a field provides crucial insights into Ganymede's interior structure and its long-term thermal evolution. This magnetic cocoon offers a measure of protection from Jupiter's intense radiation belts, subtly influencing the moon's interaction with its giant parent planet. It is a quiet, yet powerful indication of a complex, active interior, making Ganymede not just a large moon, but a truly unique and dynamic celestial body. The gentle hum of its internal dynamo creates an imperceptible boundary, shaping its environment in the vastness of space with a delicate touch. Drifting to the distant reaches of our solar system, we encounter Triton, Neptune's largest and most intriguing moon. What makes Triton particularly remarkable is its retrograde orbit. It circles Neptune in the opposite direction of the planet's rotation. This unusual orbital dance is a strong indicator that Triton did not form alongside Neptune, but was instead a captured object, likely a dwarf planet from the Kuiper belt. Its gravitational embrace by Neptune was a slow, majestic event, unfolding over billions of years, transforming its path and making it a permanent companion. This capture event explains many of Triton's unique features, including its active cryovolcanism, where plumes of nitrogen ice and dust gently erupt from its surface. The serene, backward journey of Triton reminds us that not all moons are born of their parent planets. Some are adopted wanderers, bringing their own distinct histories and characteristics to their new homes, patiently orbiting in a placid cosmic ballet. Finally, we return to Jupiter to observe one of its most striking moons, Io. This vibrant satellite holds the title of the most volcanically active body in our entire solar system. Its surface is a constantly changing tapestry of hundreds of active volcanoes, gently spewing sulfur and silicate lava. The immense tidal forces exerted by Jupiter and its other large moons, Europa, Ganymede, and Callisto, patiently flex Io's interior, generating tremendous heat. This internal warmth fuels the relentless volcanic eruptions, which continuously resurface the moon, erasing craters almost as quickly as they form. The constant quiet flow of lava and the soft expulsion of volcanic gases create a vivid, multicolored landscape, a testament to the powerful yet natural gravitational interactions within the Jovian system. Io's ceaseless geological activity is a dramatic yet measured process, revealing the profound influence of a giant planet on its close companions. Its fiery heart beats in a steady rhythm, a cosmic forge of new terrain, perpetually renewing its surface. Journeying further into Saturn's expansive system, we encounter Iapetus, a moon of truly singular beauty, marked by a dramatic two-tone appearance. One hemisphere of Iapetus is remarkably dark, almost as profound as soot, absorbing much of the sunlight that touches its surface. In stark, elegant contrast, the other hemisphere shines with a brilliance akin to freshly fallen snow, reflecting a significant portion of the sun's gentle rays. This striking duality creates a subtle yet profound boundary across its midsection, a quiet dividing line between light and shadow. Scientists believe this unique coloration arises from a combination of factors. The leading hemisphere, as Iapetus orbits Saturn, slowly sweeps up dark, dusty material originating from other distant moons, such as Phoebe, which sheds a faint ring of dark particles. Over eons, this accumulation subtly darkens the icy surface. Additionally, solar heating might play a role, gently warming the darker areas, causing any underlying ice to sublimate and reveal even more dark material, while the brighter side retains its pristine, reflective, icy crust. This delicate balance of external influence and internal process results in a moon that presents two distinct faces to the cosmos, a serene marvel of celestial art. Its tranquil, contrasting surfaces invite a quiet contemplation of the subtle forces that shape these distant worlds. The boundary between its bright and dark regions is not sharp or abrupt, but a gradual, measured transition, like a gentle fading of twilight into night, or dawn breaking over a slumbering landscape. This remarkable moon, with its elegant monochrome division, sails through space as a testament to the intricate and sometimes surprising ways in which celestial bodies are sculpted by their environment and their own quiet internal workings. The sheer difference in reflectivity between its two halves is one of the most visually captivating features in the entire solar system, a silent testament to its unique cosmic journey. This distinct characteristic makes Iapetus a placid study in contrasts, a celestial canvas painted by the gentle hand of cosmic processes. Its existence reminds us of the endless variety and unexpected beauty found within the vast, tranquil expanse of space. The subtle interplay of light absorption and reflection on its surface tells a story of distant cosmic dust and patient solar warming. A quiet narrative etched onto an icy sphere. Astronomers continue to study this captivating moon, piecing together the subtle nuances of its formation and evolution, all gently revealed through its striking appearance. Not far from Iapetus, another of Saturn's moons, Hyperion reveals an equally mesmerizing, yet entirely different, kind of cosmic oddity. Hyperion possesses a highly irregular, almost angular shape, unlike the more common spherical forms of larger moons. Its surface is deeply pockmarked with craters, giving it a distinctive, spongy appearance, as if it were a colossal, porous rock drifting through space. This unique texture, combined with its non-spherical form, contributes to another fascinating characteristic: its chaotic rotation. Unlike most moons that are tidally locked or exhibit predictable rotational patterns, Hyperion tumbles unpredictably through space. Its axis of rotation constantly shifts and changes, never settling into a stable orientation. Imagine a celestial body performing a slow, erratic dance, gently turning and spinning in an almost random fashion. This unpredictable tumbling is a direct consequence of its irregular shape and the complex gravitational influences from Saturn and its larger moons. The forces acting upon it are not uniform, leading to a gentle yet ceaseless reorientation of its body. This chaotic spin means that no 2 days on Hyperion would ever be quite the same, as the sun would rise and set from ever-changing directions. Scientists study Hyperion's peculiar motion to understand the intricate dynamics of celestial mechanics in multi-body systems. Its unusual shape and serene yet chaotic rotation make it a true marvel, a quiet testament to the diverse and sometimes unexpected outcomes of cosmic formation. This moon is a tranquil anomaly, a silent, porous wanderer, defying the typical expectations of lunar behavior with its measured, unpredictable ballet. Its surface, resembling a cosmic sponge, absorbs and reflects light in myriad ways as it slowly turns, creating ever-shifting patterns of light and shadow, a truly placid and curious sight for any distant observer. The gentle, unhurried tumble of Hyperion through the vastness of space speaks to the subtle complexities that can arise even in the most serene cosmic environments. Turning our gaze inward towards the red planet, Mars, we find its inner moon, Phobos, engaged in a slow, yet inevitable, cosmic waltz towards its parent. Phobos is a small, irregularly shaped moon, orbiting incredibly close to Mars. This proximity means that it is gradually, almost imperceptibly, drawing nearer to its parent planet. The subtle gravitational tug-of-war between Mars and Phobos is causing the moon's orbit to decay, slowly tightening its spiral inwards by about 6.5 feet each century. This measured approach means that, over the course of tens of millions of years, Phobos will face one of two gentle destinies. It might peacefully break apart, its material gently dispersing to form a temporary, diffuse ring system around Mars. This ring would be a transient beauty, slowly scattering its particles over time. Alternatively, it could experience a soft, unhurried impact with the Martian surface, its fragmented remnants settling gently into the planet's crust. This cosmic evolution is a natural, non-dramatic process, a testament to the patient, persistent forces of gravity. There will be no catastrophic collision in the violent sense, but rather a graceful disintegration or a gentle merging, as the moon's material returns to become part of its parent world. Phobos's quiet, inward journey is a poignant reminder of the continuous, unhurried reshaping of our solar system's celestial bodies, a placid narrative of cosmic change unfolding over immense timescales. Its fate is a testament to the subtle yet powerful influence of tidal forces, patiently guiding its descent towards a new form. This small moon's measured approach towards its planet offers a serene glimpse into the long, slow dance of gravitational interaction, a quiet lesson in the impermanence of cosmic structures. Closer to home, our own familiar moon is also engaged in a subtle yet significant cosmic ballet with Earth. While Phobos is drawing closer to Mars, our moon is, in fact, slowly drifting farther away from our planet. This leisurely recession occurs at a rate of approximately 1.5 inches per year, a barely perceptible shift over human timescales, but a profound movement over geological eras. This gradual increase in distance is a consequence of the gentle tidal forces exchanged between Earth and the Moon. As the Moon's gravity pulls on Earth's oceans, it creates tidal bulges. Earth's rotation carries these bulges slightly ahead of the Moon's direct line, and their gravitational pull subtly accelerates the Moon in its orbit, causing it to spiral outward. In return, the Moon's drag on these bulges acts as a brake on Earth's rotation, gradually lengthening our days. This delicate transfer of angular momentum is a beautiful example of the interconnectedness of celestial mechanics, a serene and patient interaction shaping both our planet and its loyal companion. Over billions of years, this slow recession will continue, gently altering the dynamics of our Earth-Moon system. The Moon's quiet, outward journey is a testament to the enduring, subtle power of gravitational interaction, a continuous, unhurried reshaping of our immediate cosmic neighborhood. This measured separation is a natural part of their shared cosmic history, a gentle expansion of their bond, illustrating the placid, long-term evolution of planetary systems. It is a quiet reminder that even the most stable relationships in the cosmos are subject to slow, graceful change, a constant, imperceptible dance of separation and influence. Returning to the majestic system of Saturn, another of its prominent moons, Rhea, has presented scientists with an intriguing possibility: the potential existence of a faint ring system of its own. While Saturn itself is renowned for its spectacular expansive rings, the idea of a moon possessing such a feature is truly unique and would represent a gentle marvel in our solar system. The evidence for Rhea's proposed rings came from observations of electron depletion in its vicinity, suggesting that material was absorbing electrons from Saturn's magnetosphere in a pattern consistent with a subtle, tenuous disk. If confirmed, these rings would not be the grand, icy structures of Saturn, but rather faint, diffuse bands of dust and small debris, perhaps formed from the gentle breakup of a smaller satellite or from material ejected from Rhea's surface. This delicate, almost imperceptible ring system would orbit Rhea, a silent, ethereal halo around the icy moon. The presence of such a subtle structure would offer fascinating insights into the complex dynamics of moon formation and the quiet, continuous processes of material redistribution within planetary systems. It challenges our conventional understanding of where rings can form and persist, hinting at a more intricate and varied cosmic landscape than previously imagined. Rhea's potential rings would be a quiet, elegant testament to the unexpected wonders that still await discovery, a truly unique feature that adds another layer of placid complexity to the already diverse tapestry of Saturn's many companions. This gentle ring-bearer, if proven, would quietly redefine our understanding of lunar environments, presenting a serene mystery for future exploration. Journeying to the distant, serene realm of Uranus, we encounter its moon Miranda, a world whose surface tells a story of remarkable, yet gentle, geological transformation. Miranda has a strikingly varied surface, appearing like a cosmic patchwork of different terrains, a jumbled collection of features that seem to have been pieced together. We observe ancient, cratered regions alongside younger, brighter areas, characterized by enormous parallel grooves and fault lines. These unique coronae, or ovoid structures, suggest past geological activity, a quiet reshaping of its crust. Scientists believe that this distinctive landscape is the result of internal processes, perhaps gentle cryovolcanism, where icy material slowly flowed onto the surface, or intense tidal stresses from Uranus's gravity in the distant past. These forces could have caused the moon's interior to warm and expand, leading to the cracking and shifting of its crust, creating a truly unique and intricate mosaic. The appearance of Miranda's surface is not one of violent disruption, but rather a slow, patient rearrangement of its icy shell, a testament to its internal evolution. This patchwork of features reveals a history of subtle yet profound geological events, creating a moon that is unlike any other. Miranda's serene, jumbled surface is a quiet invitation to ponder the diverse ways in which small celestial bodies can evolve, a beautiful, tranquil mystery drifting in the outer solar system. Its gentle, mosaic-like appearance speaks of a long history of measured internal dynamism, creating a landscape that is both perplexing and profoundly elegant. The subtle variations in its surface geology offer a placid record of its past, inviting us to slowly unravel its secrets. Continuing our journey through the diverse tapestry of celestial companions, we turn our attention to the distant dwarf planet Pluto and its largest moon, Charon. This remarkable duo is often considered not merely a planet and its satellite, but rather a binary system, a unique pairing in our cosmic neighborhood. The reason for this special designation lies in Charon's substantial size relative to Pluto. Charon is so large, almost half the diameter of Pluto itself, that their combined gravitational pull causes them to orbit a point in space that actually lies between them, rather than Charon orbiting directly around Pluto's center. This shared center of mass, known as the barycenter, orchestrates their elegant, perpetual dance. Instead of one body circling another, they both gently weave around this invisible point, locked in a stable, unhurried embrace. This placid, synchronized motion creates a beautiful orbital ballet, a testament to the powerful, yet balanced gravitational forces at play between two celestial bodies of comparable mass. Their existence as a binary system offers a serene example of how gravitational dynamics can shape the relationships between worlds, moving beyond the simple planet-moon paradigm into a more interconnected, shared journey through the silent depths of space. This cosmic waltz, performed in the distant Kuiper belt, is a subtle marvel of celestial mechanics, unfolding with a measured grace over eons. In another elegant display of gravitational influence, moons can also act as shepherds within the grand, sweeping ring systems of giant planets. Imagine the magnificent, shimmering rings of Saturn, composed of countless particles of ice and rock, each quietly orbiting the planet. Within these vast, intricate structures, small, dedicated moons subtly guide and sculpt the ring material. Using their gentle gravitational pull, these shepherd moons maintain the remarkably sharp edges of the rings and carve out distinct, clear gaps within them. They are like patient, unseen guardians, subtly corralling the billions of ring particles, preventing them from scattering too widely or collapsing into a uniform disk. Their measured orbits and delicate gravitational nudges keep the ring system organized, preserving its intricate beauty and delicate structure. Without these silent guardians, the rings would likely lose their defined forms, blurring into a less distinct band. This placid interaction between the shepherd moons and the ring particles is a continuous, unhurried process, a beautiful demonstration of how even small celestial bodies can exert a profound, elegant influence on their cosmic environment, maintaining order and structure in a vast, dynamic system. The subtle dance of these moons ensures the enduring splendor of the planetary rings, a serene spectacle for all to behold. As our understanding of the cosmos expands, so too does our curiosity about what lies beyond our immediate solar system. Scientists now theorize the existence of exomoons, which are moons orbiting planets outside our solar system, around distant stars. While their detection remains a significant challenge due to their small size and the immense distances involved, some potential candidates have already been identified, sparking serene anticipation among astronomers. The formation mechanisms that create moons in our own solar system, such as co-accretion, capture, or giant impacts, are expected to operate around exoplanets as well. Therefore, it is considered highly probable that many of the thousands of exoplanets discovered so far host their own families of natural satellites. Detecting these elusive exomoons often involves patiently observing subtle dips in starlight as an exoplanet transits or passes in front of its star, looking for additional, even tinier dips or variations that might be caused by an accompanying moon. The quiet pursuit of these distant celestial companions opens up a new frontier in astronomy, promising to reveal an even greater diversity of worlds and their intricate orbital dance. The potential discovery of a truly Earth-like exomoon, perhaps harboring its own subsurface ocean or a unique atmosphere, inspires a profound sense of wonder about the placid, unknown possibilities that patiently await discovery across the vast interstellar medium. Closer to our home, Earth's own moon holds a special distinction, not only for its familiar presence in our night sky, but also for its unique origin and significant size. Our moon is believed to have formed from a colossal, yet formative event, a giant impact between the early Earth and a Mars-sized celestial body, sometimes referred to as Theia. This gentle, transformative collision, occurring billions of years ago, ejected a vast amount of material into orbit around our nascent planet. Over time, this debris slowly coalesced under its own gravity, patiently forming the moon we know today. What makes our moon truly unique is its exceptionally large size relative to its parent planet. Compared to other moons in the solar system, which are often much smaller than their host planets, Earth's moon is remarkably substantial. This generous proportion has profound implications, subtly influencing Earth's tides and, importantly, stabilizing our planet's axial tilt. This stability has, in turn, contributed to Earth's relatively stable climate over geological timescales, a serene and crucial factor in the long, unhurried development of life. The moon's grand scale is a silent testament to the gentle, yet powerful processes of planetary formation, a constant, comforting presence in our sky, quietly shaping our world. Its substantial mass and the story of its birth make it a placid and profound companion, integral to Earth's enduring cosmic narrative. Revisiting Europa, Jupiter's enigmatic icy moon, we delve deeper into the source of its potential for life. The hidden ocean beneath Europa's crust is thought to be warmed by persistent tidal forces from its colossal parent planet, Jupiter. As Europa orbits Jupiter, the immense gravitational pull of the giant planet subtly stretches and squeezes the moon's interior. This gentle, yet constant flexing creates internal friction, patiently generating heat deep within Europa. This process, known as tidal heating, acts as a crucial internal energy source, preventing the moon's subsurface ocean from freezing solid. It's a natural, quiet warmth, akin to the gentle kneading of dough, continuously maintaining the liquid state of the vast ocean beneath the ice. This internal heat is particularly significant because it could power hydrothermal vents on Europa's seafloor, similar to those found on Earth's ocean floors. These vents release chemical-rich fluids, providing a potential energy source for chemosynthetic life, independent of sunlight. The steady, unhurried rhythm of Jupiter's gravitational pull thus creates and sustains a placid, potentially life-supporting environment, far from the sun's direct warmth. This delicate balance of forces underscores the subtle ways in which distant worlds can harbor the ingredients for life, a serene and profound possibility. Turning our gaze back to Titan, Saturn's largest moon, we recall its truly unique and complex atmosphere. This dense, orange veil is predominantly rich in nitrogen, much like Earth's atmosphere, but it also contains significant amounts of methane. This methane, under the chill conditions of the outer solar system, behaves much like water does on Earth, creating an intricate and fascinating cycle. On Titan, we find serene methane clouds drifting across its hazy skies, eventually releasing gentle methane rain that falls upon its frigid surface. This precipitation feeds into meandering methane rivers that carve quiet channels through its landscape, eventually flowing into vast, tranquil lakes and expansive seas. These liquid methane bodies shimmer under the distant sunlight, reflecting the hazy sky in a placid mirror. The entire process forms a complete, if alien, hydrological cycle, a patient and continuous transformation of liquids and gases. Titan offers a breathtaking parallel to Earth's water cycle, but with a different chemical foundation, providing a window into the diverse forms that planetary processes can take. This unique, serene world, with its hydrocarbon clouds and liquid seas, is a testament to the boundless creativity of the cosmos, quietly demonstrating the myriad ways in which planets and moons can evolve and sustain dynamic environments. And returning one last time to Jupiter's inner realm, Io continues to amaze with its unparalleled geological activity. This remarkable moon is indeed a true cosmic powerhouse of internal heat. Its surface is a constantly evolving canvas, adorned with hundreds of active volcanoes that gently, yet ceaselessly, erupt. These volcanoes spew forth vast quantities of molten sulfur and silicate lava, which flow across its surface, often creating vivid, multicolored plains and mountains. The primary driver of this extraordinary activity is the intense tidal heating generated by Jupiter's colossal gravitational pull, in concert with the subtle gravitational nudges from Europa and Ganymede. These forces patiently flex and deform Io's interior, creating immense friction and generating so much heat that the moon's rocky mantle remains partially molten. This internal warmth continuously fuels the eruptions, ensuring that Io's surface is perpetually renewed, erasing impact. Unhurried outflow of material ensures that Io remains a geologically young world, a vibrant, living, a truly placid and powerful display of planetary dynamism. Venturing beyond these well-formed spherical satellites, we discover a different class of moons, particularly prevalent in the outer solar system. Many of the small, irregularly shaped moons that quietly orbit the gas giants are believed to be captured asteroids or comets. These celestial wanderers, once independently traversing the vastness of space, were gently drawn into the gravitational embrace of a massive planet. Unlike moons that form alongside their parent planets from a shared disk of material, these captured bodies retain their original, often jagged and non-spherical forms. Their irregular shapes are a silent testament to their origins as fragments of larger bodies or as primordial debris, never having possessed enough self-gravity to pull themselves into a smooth, rounded sphere. The process of capture is not a violent snatch, but a slow, patient gravitational dance, where a passing asteroid or comet gradually loses energy and settles into a stable orbit around a more massive world. This elegant process often results in moons with highly inclined or retrograde orbits, further hinting at their alien origins. These numerous small dark companions are like cosmic pebbles, silently circling their giant hosts, each carrying a story of a long journey through the early, more chaotic solar system. They serve as quiet reminders of the gentle, yet persistent, gravitational forces that continuously reshape and populate planetary systems. Their presence adds a layer of subtle complexity to the moon families of the outer planets, offering scientists a placid window into the history of orbital dynamics and the gentle, unhurried collection of celestial debris. Each irregular contour on their surfaces whispers of eons spent drifting through space before their quiet adoption into a new, larger family. The serene irregularity of these captured worlds offers a beautiful contrast to the more perfectly spherical moons, highlighting the diverse pathways of cosmic formation and evolution. Among Saturn's many companions, two small moons, Janus and Epimetheus, perform a particularly graceful and intricate orbital ballet. These two moons share nearly identical orbits, circling Saturn at almost the exact same distance. Rather than colliding, which their close proximity might suggest, they engage in a fascinating and periodic swap of positions. Approximately every 4 years, as the inner moon slowly gains on the outer moon, their gentle gravitational interaction causes them to exchange orbital energies. The inner moon quietly nudges the outer moon into a slightly higher orbit, while itself dropping into the lower one. This subtle exchange then reverses their relative speeds, allowing the process to repeat itself in a serene, rhythmic cycle. This elegant gravitational dance prevents any direct impact, allowing both moons to peacefully coexist in their shared orbital path. It is a precise and unhurried negotiation of gravitational forces, a testament to the intricate stability that can arise in complex celestial systems. This quiet, measured swapping of positions is a beautiful example of orbital resonance, a subtle yet powerful mechanism that maintains harmony among celestial bodies. Janus and Epimetheus drift through space, patiently exchanging their places, a perpetual, placid dance that highlights the delicate precision of the cosmos. Their synchronized movement, a silent, graceful exchange, is a continuous performance, revealing the subtle ways in which celestial neighbors interact without disruption. This quiet, careful choreography speaks to the profound elegance of gravitational physics, allowing these two small moons to share a nearly identical cosmic path in perfect, unhurried harmony. Returning to Io, the most volcanically active moon, its extraordinary geological dynamism is, at its heart, a direct consequence of the immense tidal flexing caused by Jupiter's powerful gravity. As Io ceaselessly orbits its giant parent, Jupiter's colossal gravitational pull subtly stretches and compresses the moon's interior. This continuous rhythmic distortion, a gentle kneading of its rocky core and mantle, generates an enormous amount of internal friction. This friction, in turn, produces intense heat deep within Io, keeping much of its interior molten. It is this internal warmth, patiently and perpetually generated by Jupiter's tidal forces, that fuels the moon's hundreds of active volcanoes. Without this constant gravitational massage, Io would likely be a cold, geologically inactive world, much like our own moon. Instead, it is a vibrant, fiery sphere, its surface constantly remade by gentle eruptions of sulfur and silicate lava. The tidal flexing is not a violent ripping apart, but a slow, consistent deformation, a natural process that transforms gravitational energy into thermal energy. This placid yet powerful interaction ensures Io remains a dynamic, ever-changing world, a testament to the profound influence a giant planet can exert on its close-knit companions. The subtle pull and release of gravity orchestrate a continuous, unhurried geological spectacle. The unending dance of expansion and compression within Io's depths generates a constant supply of heat, allowing its inner fires to burn with a steady, measured intensity, making it a unique and awe-inspiring world. Shifting our focus to Europa, we marvel at its remarkably smooth surface, a feature that distinguishes it from many other cratered worlds. The icy crust of Europa shows surprisingly few large impact craters, especially when compared to ancient, heavily pockmarked bodies like our Moon or Jupiter's Callisto. This relative absence of craters is a strong indication of active resurfacing processes. Scientists believe that Europa's surface is continuously, yet gently, being renewed, erasing the scars of past impacts. This placid resurfacing could occur through several mechanisms, such as the slow flow of warm ice from beneath the surface, or the subtle upwelling of liquid water from the vast subsurface ocean through cracks in the ice. These gentle geological activities effectively smooth out the moon's exterior, maintaining its pristine, unblemished appearance. The surface is not static, but a quiet living crust, subtly shifting and reforming over geological timescales. This constant, unhurried renewal of its icy shell is a key piece of evidence supporting the existence of the deep, liquid ocean beneath, a world kept active and dynamic by internal warmth. Europa's serene, unmarred surface is a beautiful testament to its hidden internal activity, a placid canvas upon which the subtle forces of its interior are continuously at work. The gentle, almost imperceptible movements of its icy shell speak volumes about the hidden liquid world below, hinting at a quiet, continuous process of renewal and transformation. As we further explore the implications of subsurface oceans, Enceladus, Saturn's small active moon, continues to captivate with its dramatic plumes. The material gracefully ejected from Enceladus's southern polar region, particularly from its distinctive tiger stripes, offers a direct window into its hidden depths. Within these plumes, scientists have detected a fascinating array of compounds: organic molecules, various salts, and even tiny grains of silica. The presence of organic molecules, which are carbon-based compounds, is especially significant, as these are the fundamental building blocks of life as we know it. Salts suggest that the subsurface ocean is interacting with a rocky core, potentially leading to chemical reactions that could provide energy. Silica grains, which form only at relatively high temperatures, indicate that hot hydrothermal activity might be occurring on Enceladus's seafloor, similar to the vents found in Earth's deep oceans. These findings collectively point to a potentially habitable environment within Enceladus's subsurface ocean. These ingredients, gently wafting into space, are considered profoundly important for the emergence and sustenance of life. The quiet, consistent release of these rich compounds makes Enceladus a prime candidate in the search for extraterrestrial life, a placid beacon of potential biological activity. The subtle composition of its plumes whispers of a hidden, active world, patiently nurturing the conditions for life far beneath its icy shell. The gentle expulsion of these vital components into space is a profound, unhurried revelation of its inner workings, a testament to the potential for life in unexpected corners of the cosmos. Journeying back to Jupiter's largest moon, Ganymede, we observe a surface that beautifully chronicles its long and varied geological history. Ganymede's icy surface displays a striking dichotomy. It features both ancient, heavily cratered regions and younger, brighter areas characterized by intricate grooved terrains. The ancient, dark regions are densely packed with impact craters, silent witnesses to billions of years of cosmic bombardment, preserving a record of the early solar system. In elegant contrast, the younger, lighter grooved terrains are marked by long, parallel ridges and valleys, forming complex patterns that suggest past tectonic activity or cryovolcanism. These grooved areas are thought to have formed when internal forces gently stretched and fractured Ganymede's icy crust, allowing warmer, perhaps slushy, material to slowly rise and resurface the moon. This placid geological evolution indicates that Ganymede was once, or perhaps still is, an internally active world, capable of reshaping its own exterior. The contrast between these two distinct types of terrain tells a serene story of continuous transformation and patient geological processes. Ganymede's surface is a magnificent, unhurried tapestry woven with threads of ancient history and more recent renewal, a testament to its enduring dynamism. The subtle interplay of light and shadow across these varied landscapes reveals a moon that has gracefully evolved over immense stretches of cosmic time, a silent, majestic record of its profound journey. Its diverse face, a mosaic of old and new, offers a tranquil canvas for understanding the patient, unfolding history of large, icy satellites. From these grand, active worlds, we now gently shift our gaze inward to the red planet, Mars, and its two diminutive companions, Phobos and Deimos. These intriguing celestial bodies stand in quiet contrast to the majestic, spherical moons of the outer solar system. They are small, distinctively potato-shaped objects, with irregular contours and surfaces that bear the subtle marks of countless ancient impacts. Their peculiar forms and diminutive sizes, measuring only a few miles across, strongly suggest that they are not native to Mars, but rather resemble captured asteroids or perhaps fragments of a larger body that was gently broken apart. Scientists believe that, eons ago, these cosmic wanderers drifted too close to the gravitational embrace of the red planet. In a slow, unhurried process, Mars's subtle pull gradually captured them, drawing them into stable, yet irregular orbits. They are like quiet, stony echoes of the asteroid belt, now faithfully circling a new home. Their surfaces are dark and heavily cratered, reflecting a long history of cosmic journeys before their peaceful adoption into the Martian system. The very appearance of Phobos and Deimos, with their rugged, non-spherical shapes, speaks volumes about their origins, telling a silent tale of distant travels and a gentle gravitational capture that forever altered their paths. They are truly placid anomalies among the more common, rounded satellites, each a unique testament to the varied ways in which planets acquire their celestial companions. Their irregular forms, patiently sculpted by eons of cosmic impacts, highlight the subtle differences in lunar evolution across our solar system, offering a tranquil glimpse into the quiet mechanics of celestial acquisition. Closer to home, our own familiar moon, Earth's steadfast companion, exerts a profound yet gentle influence on our planet's watery surface. The moon is the primary cause of Earth's tides, a gentle rhythmic pull that subtly shapes our oceans, leading to the predictable rise and fall of sea levels along our coastlines. As the moon orbits Earth, its gravity gently pulls on the oceans, creating bulges of water on both the side of Earth facing the moon and on the opposite side. The solid Earth is also subtly stretched, but the more fluid water responds more dramatically. As Earth rotates beneath these bulges, coastal areas experience 2 high tides and 2 low tides each day. This continuous, unhurried gravitational interaction is a beautiful demonstration of celestial mechanics at work, a silent, powerful connection between our planet and its satellite. The moon's delicate, yet persistent, gravitational embrace ensures the ceaseless, placid ebb and flow of our planet's vast waters, a fundamental rhythm of life on Earth. This gentle lunar dance has shaped coastlines, influenced marine ecosystems, and provided a steady, predictable pulse for our planet for billions of years. A serene testament to the enduring influence of our cosmic neighbor, the invisible threads of gravity weave a continuous, measured pattern across our world, a quiet symphony played out in the depths of our oceans, all orchestrated by the presence of our moon. Journeying back, revisit the dwarf planet Pluto and its large moon, Charon. Charon's surface presents a mysterious and intriguing feature, a distinct red polar cap. This enigmatic coloration, located at its northern pole, stands out against the moon's otherwise grey and icy landscape. Scientists believe this unusual crimson hue is possibly formed by atmospheric gases escaping from Pluto itself. As Pluto orbits the Sun, its atmosphere, composed mainly of nitrogen, methane, and carbon monoxide, subtly expands and contracts. During periods when Pluto is closer to the Sun, its atmosphere thaws and expands. As it moves farther away, some of these gases, particularly methane, can gently escape Pluto's gravitational pull and drift toward Charon. Once these escaping methane molecules reach Charon's frigid North Pole, they become trapped and freeze onto the surface. Over eons, this frozen methane is then subtly processed by ultraviolet radiation from the Sun, transforming it into more complex, reddish-brown organic molecules called tholins. This slow, patient process creates the distinctive red polar cap, a silent, colourful record of the subtle atmospheric exchange between Pluto and its largest moon. Charon's mysterious crimson crown is a placid reminder of the interconnectedness of these distant, icy worlds, a beautiful, unhurried chemical narrative unfolding in the quiet depths of the Kuiper Belt. This subtle, almost imperceptible transfer of material paints a unique, tranquil landscape, revealing the delicate interplay of distant light and frozen gases. As we consider the vast array of moons across our solar system, it is worth pausing once more to acknowledge the sheer grandeur of Ganymede, Jupiter's most massive moon. It holds the undeniable distinction of being the largest known moon in our entire solar system. To truly appreciate its scale, one must consider its impressive diameter, which spans over 3,200 miles. This immense size places Ganymede not only above all other moons, but also surpasses the dimensions of the planet Mercury and the dwarf planet Pluto. Its colossal presence makes it a truly planetary-scale object, a world in its own right, capable of sustaining its unique magnetic field and undergoing complex geological processes. The vastness of Ganymede's icy surface, stretching across such an incredible expanse, speaks to the immense scale that can be achieved by natural satellites orbiting giant planets. Its serene, grand form, patiently shaped over billions of years, is a testament to the powerful gravitational forces and the abundant materials available in the early solar nebula. This magnificent moon drifts through the Jovian system, a silent, colossal sentinel, quietly commanding attention with its sheer magnitude and intricate surface features. Its impressive diameter is a placid reminder of the diverse and often surprising sizes found within the cosmic tapestry of moons, each a unique world waiting to be explored and understood in its unhurried celestial journey. Our own moon, a constant presence in our night sky, exhibits a fascinating orbital characteristic known as tidal locking. This means that the same side of the moon always faces our planet. From Earth, we are perpetually presented with the familiar face of the moon, while its far side remains hidden from direct view, only revealed through the patient exploration of spacecraft. This synchronous rotation is not a mere coincidence, but a natural outcome of the gentle, persistent gravitational interaction between Earth and the Moon over billions of years. The Earth's gravity has subtly pulled on the Moon, causing its rotation to gradually slow down until its rotational period matched its orbital period. It is a stable, unhurried state, a gravitational equilibrium achieved through eons of delicate tidal forces. This placid, synchronized dance ensures that the Moon keeps one face perpetually turned towards us, a faithful companion in its slow journey around our world. The constant visibility of the near side has deeply influenced human culture and mythology, while the far side remained a serene mystery for most of human history. This elegant phenomenon of tidal locking is a silent testament to the enduring and subtle power of gravity, patiently orchestrating the orbital mechanics of our immediate cosmic neighborhood. It highlights the profound, yet imperceptible ways in which celestial bodies influence each other's movements and rotations, creating a stable and enduring cosmic relationship. Considering the vast array of moons we have explored, it becomes clear that these celestial companions can form through several distinct and elegant pathways. Scientists categorize moon formation into three primary ways: co-accretion, capture, or a giant impact. Each of these methods involves a unique set of gentle cosmic processes, patiently shaping the birth of a satellite. Co-accretion describes moons that form from the same swirling disk of gas and dust that gives rise to their parent planet, growing together in a synchronized dance. Capture involves an existing celestial body, such as an asteroid or comet, being gently drawn into a planet's gravitational embrace, becoming an adopted moon. Finally, a giant impact refers to a more dramatic, yet still formative collision between a young planet and another large body, with the ejected debris slowly coalescing to form a new moon. These three pathways represent the fundamental, unhurried mechanisms through which planets acquire their diverse retinues of satellites, each method leaving its own subtle imprint on the Moon's characteristics and orbital properties. Understanding these different origins helps astronomers decipher the long, placid history of planetary systems and the gentle processes that have shaped the worlds we observe today. Delving deeper into the first of these formation mechanisms, co-accretion describes a process where a moon forms directly from the same swirling disk of material that coalesced to create its parent planet. Imagine a young, nascent planet slowly gathering material from a vast, rotating cloud of gas and dust in the early solar system. Within this same protoplanetary disk, smaller clumps of material also begin to gently aggregate and grow in orbit around the forming planet. These smaller clumps, through patient gravitational attraction, slowly accrete more and more dust and gas, gradually building up into a moon. This process is a synchronized, unhurried growth, with the Moon and its parent planet forming side by side, sharing a common birthplace. The resulting moons typically orbit in the same direction as their planet's rotation, and often lie in the planet's equatorial plane, reflecting their shared origin from the flat, spinning disk. This method of formation is characteristic of many of the large, regular moons of the giant planets, such as Jupiter's Galilean moons, which patiently gathered their mass from the circumplanetary disks that surrounded the gas giants. Co-accretion is a serene and elegant process, a beautiful example of simultaneous growth and shared destiny in the quiet nurseries of star systems. The gentle gathering of cosmic dust and gas over immense stretches of time slowly sculpts both planet and moon from the same primordial matter, creating a harmonious and placid orbital relationship. Beyond the serene process of co-accretion, another significant pathway for moon formation involves the gentle embrace of a celestial wanderer. Captured moons are typically asteroids or comets that, in their long, unhurried journeys through the solar system, drifted too close to a massive planet. Instead of passing by or colliding directly, these independent bodies were slowly, patiently drawn into the planet's gravitational embrace, eventually settling into stable orbits. This subtle gravitational gradual process, where the planet's gravity gently saps energy from the passing object, allowing it to become a permanent companion. These captured satellites often retain their irregular shapes and composition, reflecting their original lives as independent, small solar system bodies. Their orbits can also be highly inclined, meaning they don't necessarily lie in the same plane as the planet's equator, or even retrograde, orbiting, further hinting at their external origin. The outer planets, with their vast gravitational spheres of influence, are particularly adept at this gentle form of acquisition, quietly collecting a diverse retinue of these small, stony or icy wanderers. Each captured moon tells a silent story of a distant journey, a placid testament to the subtle, yet powerful, gravitational interactions that continuously shape and populate our solar system. They are like cosmic souvenirs, patiently brought into a new family, adding to the rich tapestry of celestial diversity. Their presence offers a tranquil glimpse into the dynamic, unhurried evolution of planetary systems, where even fleeting encounters can lead to lasting celestial bonds. The slow, persistent pull of a giant world can transform a solitary asteroid into a loyal satellite, a quiet act of cosmic adoption. The third, and perhaps most dramatic pathway for moon formation, is through a giant impact. This scenario, famously proposed for the birth of Earth's own moon, involves a large object gently colliding with a young, still-forming planet. Picture a nascent Earth, billions of years ago, when the solar system was a more crowded and dynamic place. Embarked on a slow, unhurried collision course with our early planet. This immense, yet formative impact was not a destructive catastrophe in the sense of obliterating both bodies, but rather a transformative event. The collision gently fragmented and melted vast amounts of material from both the impactor and the early Earth, ejecting a swirling cloud of superheated debris into orbit around our planet. Over an extended period, this orbiting material slowly, patiently, coalesced under its own gravity. The countless particles of rock and molten rock gently drew together, gradually building up the moon we see today. This process of slow accretion from impact debris resulted in a moon that is large relative to its parent planet and shares a similar isotopic composition to Earth, yet is depleted in volatile elements due to the intense heat of the impact. The giant impact hypothesis offers a serene explanation for the moon's unique characteristics, illustrating how even a momentous cosmic event can lead to a stable, placid outcome, shaping the long-term evolution of a planetary system. It is a quiet narrative of creation, born from a profound, yet gentle, cosmic encounter, forging a lasting bond between two celestial bodies. The slow, measured gathering of ejected fragments into a new spherical satellite is a beautiful testament to the universe's capacity for intricate, self-organizing processes. As we survey the planets of our solar system, we observe a fascinating diversity in their lunar families. The inner planets, Mercury and Venus, stand out in their serene solitude as they have no moons. These two worlds, closest to the Sun, orbit without any natural satellites. Scientists believe this absence is likely due to their proximity to the Sun. The Sun's powerful gravitational influence makes it challenging for these planets to either form moons through co-accretion or to capture passing asteroids. Any material that might have formed a moon would have been easily swept away by the solar wind or disrupted by the Sun's tidal forces. Furthermore, any captured objects would find it difficult to maintain stable orbits against the Sun's dominant pull. Mercury and Venus thus drift through space as solitary spheres, their skies unadorned by the gentle glow of a lunar companion. Their moonless state offers a quiet contrast to the more populous outer solar system, highlighting the varied conditions that dictate the presence or absence of natural satellites. This tranquil solitude is a unique characteristic, patiently observed, that speaks to the delicate balance of gravitational forces in the inner solar system, where the Sun's influence reigns supreme, preventing the formation or retention of any celestial companions. Their calm, unburdened orbits are a testament to the singular paths these planets have taken through cosmic history. Moving slightly farther from the Sun, we encounter Mars, which possesses two small moons, Phobos and Deimos. As previously discussed, these two companions are believed to be captured asteroids, small, irregularly shaped bodies that were gently drawn into orbit around the red planet. Their diminutive size and non-spherical forms underscore their distinct origin compared to the larger, more regularly formed moons of the outer planets. Phobos, the inner moon, orbits incredibly close to Mars, completing a full circuit in just over 7 hours. Deimos, the outer moon, takes a more leisurely 30 hours to complete its orbit. Both moons are dark and heavily cratered, silent witnesses to countless impacts throughout their long histories. Their presence, though modest, adds a subtle complexity to the Martian sky, offering two distinct lunar companions to an observer on the planet's surface. The quiet presence of Phobos and Deimos reminds us that not all moons are grand, spherical worlds. Some are humble, stony companions, patiently circling their host planet in a serene, unhurried dance. Their small scale and irregular shapes offer a tranquil glimpse into the more subtle gravitational processes that shape the inner solar system's planetary families, a quiet testament to the variety of celestial relationships found throughout the cosmos. Venturing into the realm of the gas giants, Jupiter, the colossal king of our solar system, boasts an impressive and ever-growing retinue of natural satellites. Jupiter has at least 95 known moons, making it a true planetary system unto itself. This vast collection includes the 4 massive Galilean moons, Io, Europa, Ganymede, and Callisto, which are large enough to be worlds in their own right, along with dozens of smaller, more distant, and often irregularly shaped moons. The discovery of new Jovian moons is an ongoing process, as improved telescopes and observational techniques patiently reveal more of these faint, distant companions. Many of these newly discovered moons are believed to be captured asteroids, slowly orbiting Jupiter in distant, often eccentric paths. The sheer number of Jupiter's moons speaks to its immense gravitational power and its long history of gently attracting and holding on to celestial wanderers. This placid, diverse family of satellites forms a miniature solar system, each moon engaged in its own unhurried orbital journey around the giant planet. The extensive lunar system of Jupiter offers a tranquil laboratory for studying a wide range of celestial phenomena, from intense volcanic activity to the potential for subsurface oceans, all under the powerful yet silent influence of the gas giant. The constant, quiet interplay of gravity among these 95 worlds creates a complex and dynamic system, a serene testament to the richness and intricacy of our solar system's largest planet. Each of these moons, whether large or small, regular or irregular, plays a subtle role in the grand, unhurried dance around Jupiter. Even more astounding than Jupiter's prolific lunar family is that of Saturn, the ringed jewel of our solar system. Saturn has 146 known moons, making it the planet with the most natural satellites discovered so far. This truly vast collection includes iconic worlds like Titan, Enceladus, and Iapetus, alongside a multitude of smaller, often icy and irregularly shaped companions. The continuous discovery of new moons around Saturn highlights the immense gravitational sphere of influence of this ringed giant and the ongoing patient work of astronomers. Many of Saturn's newly identified moons are tiny, faint objects, often just a few miles across, believed to be captured asteroids or fragments of larger bodies. These distant small satellites typically orbit far from the planet, often with highly inclined or retrograde paths, further suggesting their captured origins. The sheer number of Saturn's moons creates an incredibly complex and dynamic system, with intricate gravitational interactions shaping their orbits and influencing the planet's magnificent rings. This placid, bustling family of moons forms a profound and serene example of celestial diversity, each moon contributing to the overall grandeur of the Saturnian system. The constant, unhurried dance of these 146 worlds around Saturn is a testament to the enduring power of gravity and the rich tapestry of objects that can be found in the outer solar system. It offers a tranquil glimpse into the intricate mechanics of a truly populous planetary system, where each moon, regardless of its size, plays a subtle yet significant role in the grand cosmic ballet. The quiet presence of so many companions underscores the gentle, persistent forces that shape the evolution of these magnificent celestial families. Venturing even farther into the tranquil depths of the outer solar system, we arrive at Uranus, the ice giant, which hosts its own distinctive family of natural satellites. Uranus has 27 known moons, a diverse and intriguing collection of icy worlds. Unlike the more numerous, irregularly shaped moons of Jupiter and Saturn, many of Uranus's moons are of moderate size, exhibiting a fascinating array of surface features. This family includes 5 major satellites: Miranda, Ariel, Umbriel, Titania, and Oberon, each a placid world with its own unique geological history. The orbits of these moons are often highly inclined, reflecting the unusual tilt of Uranus itself, which orbits the Sun on its side. This unique planetary orientation subtly influences the dynamics of its lunar companions. The moons of Uranus are primarily composed of a serene mixture of ice and rock, their surfaces bearing the silent marks of ancient impacts and past geological activity. Exploring these distant, icy worlds offers a tranquil glimpse into the formation and evolution of satellites. The gentle, unhurried dance of these 27 moons around their tilted parent planet adds a layer of quiet complexity to the cosmic tapestry, showcasing the varied ways in which celestial families arrange themselves across the vastness of space. Each of these moons, from the jumbled surface of Miranda to the darker plains of Umbriel, tells a silent story of its patient journey through cosmic time, constantly shaped by the subtle gravitational pull of Uranus. Continuing our serene exploration to the outermost reaches of the main planetary system, we find Neptune, another distant ice giant, accompanied by its own family of 14 known moons. This collection includes the majestic, retrograde orbiting Triton, which we have previously discussed, along with 13 other smaller, more distant satellites. Triton, with its substantial size and unusual backward orbit, stands out as the jewel of Neptune's lunar system, a testament to its dramatic capture from the Kuiper Belt. The remaining 13 moons are generally smaller and often irregularly shaped, many of them believed to be captured objects, similar to the distant, irregular moons of Jupiter and Saturn. Their orbits are typically distant and often highly inclined, reflecting the subtle gravitational interactions that define their paths around Neptune. These icy, silent companions drift through the dim light of the outer solar system, each patiently circling its distant parent. The study of Neptune's moons provides valuable insights into the formation of planetary systems and the gentle processes of celestial capture in the colder, more remote regions of space. The quiet, unhurried orbits of these 14 worlds around Neptune underscore the persistent, subtle power of gravity, shaping the dynamics of even the most distant planetary families. Each moon, whether a large captured wanderer or a small icy fragment, contributes to the serene complexity of the Neptunian system, a placid tableau in the cosmic expanse. Beyond the major planets, our solar system is also home to a fascinating array of smaller celestial bodies, and many dwarf planets, like the familiar Pluto, also possess moons. Pluto, though reclassified from a major planet, retains a complex and intriguing system of 5 known moons. Its largest moon, Charon, is so substantial that, as we explored earlier, they are often considered a binary system, gracefully orbiting a shared center of mass. In addition to Charon, Pluto is accompanied by 4 smaller moons: Styx, Nix, Kerberos, and Hydra. These tiny, irregularly shaped satellites are believed to have formed from the debris ejected during the same ancient, gentle collision that created Charon. Their orbits are surprisingly complex, influenced by the combined gravitational pull of Pluto and Charon, creating a delicate yet stable dance. The existence of moons around dwarf planets highlights that satellite formation is not exclusive to the grand scale of the gas giants or Earth-sized worlds. Even smaller celestial bodies can host their own families of companions, patiently orbiting in the quiet depths of space. These miniature lunar systems offer a tranquil window into the diverse ways in which gravitational forces can sculpt and organize matter, even on a smaller scale, revealing the placid, unhurried evolution of these distant icy worlds. The subtle gravitational ballet of these minor moons around their dwarf planet host speaks to the pervasive nature of celestial relationships throughout the solar system. The presence of moons extends even to the vast expanse of the asteroid belt, where rocky fragments orbit between Mars and Jupiter. It might come as a surprise, but even asteroids in this belt can have their own tiny moons. These are not grand spherical satellites, but rather smaller, often irregularly shaped rocks that gently orbit a larger asteroid. These asteroid moons are typically very small, sometimes just hundreds of feet across, and often orbit quite closely to their parent asteroid. They are believed to form through various gentle mechanisms, such as fragments being subtly dislodged from the main asteroid during a minor impact and then slowly recaptured by its gravity, or through the gentle breaking apart of a loosely bound binary asteroid. The discovery of these miniature lunar systems around asteroids has added a new layer of complexity to our understanding of the asteroid belt. It reveals that even these relatively small celestial bodies are not always solitary wanderers, but can host their own placid, tiny companions, patiently circling their host in a slow, unhurried dance. The existence of these asteroid moons offers a tranquil glimpse into the subtle gravitational interactions that occur on smaller scales throughout our solar system, showcasing the pervasive nature of satellite formation. Each tiny moon, a silent partner in a cosmic duet, underscores the intricate and varied ways in which celestial bodies are gravitationally bound. As we journey among the multitude of moons, a fundamental distinction emerges in their composition, subtly reflecting their origins and environments. Some moons are composed primarily of rock, while others are rich in ice. The rocky moons, typically found closer to the Sun or around the inner planets, like Earth's moon, are predominantly made of silicate materials and metals. Their surfaces are often dry, cratered, and rugged, a testament to their solid, stony nature. In elegant contrast, the icy moons, more common in the colder, outer solar system around the gas giants, are composed largely of water ice, often mixed with rock and other frozen volatiles like methane or ammonia. These icy worlds, such as Europa or Enceladus, can harbor vast subsurface oceans and exhibit cryovolcanism, where ice and water erupt instead of molten rock. This distinction in composition is a placid reflection of the temperature gradients in the early solar nebula. Closer to the Sun, only rocky materials could condense, while farther out, water ice and other volatiles remained frozen and abundant. The gentle variations in their makeup tell a silent story of their birth in different cosmic nurseries, patiently shaping their internal structures and surface features. This fundamental difference creates a serene diversity among moons, from the arid desolation of rocky worlds to the potentially life-sustaining oceans of icy ones. Each a unique expression of its cosmic heritage. The quiet elegance of their differing compositions underscores the vast range of environments and materials that contribute to the formation and evolution of these diverse celestial bodies. The shape of a moon often reveals insights into its history and its internal structure, with most large moons being spherical due to their own gravity. When a celestial body reaches a certain size, its own gravitational pull becomes powerful enough to overcome the internal strength of its material, gently pulling it into a nearly perfect spherical shape. This process, known as hydrostatic equilibrium, is a slow, unhurried transformation that results in the smooth, rounded forms we associate with major moons like Earth's moon, Ganymede, or Titan. The internal pressure generated by gravity evenly distributes the mass, creating a balanced, placid sphere. This spherical symmetry is a silent testament to the moon's substantial mass and its ability to act as a significant gravitational entity in its own right. It signifies a mature, well-formed body that has patiently settled into its most stable configuration. The serene, rounded contours of these large moons offer a beautiful contrast to the more jagged, irregular shapes of smaller bodies, highlighting the elegance of gravitational forces in sculpting celestial forms. Their spherical perfection is a quiet declaration of their significant size and the profound, yet gentle power of their own self-gravity. This unhurried shaping into a sphere is a fundamental aspect of large celestial bodies, revealing a consistent and elegant principle of cosmic architecture. In contrast to their larger, perfectly rounded counterparts, smaller moons often have irregular, non-spherical shapes. These diminutive celestial companions, typically only a few miles or tens of miles across, lack sufficient gravitational pull to overcome the rigidity of their rocky or icy material. Consequently, their internal forces are not strong enough to gently mold them into a smooth, spherical form. Instead, they retain the irregular, often jagged and asymmetrical shapes of their formation, resembling cosmic potatoes, pebbles, or fragments. Many of these smaller, irregularly shaped moons, or perhaps remnants from the gentle breakup of a larger body. Their non-spherical appearance is a quiet testament to their modest mass and their history of gentle impacts and gravitational nudges. They drift through space as silent, oddly shaped companions, each unique in its contours, patiently orbiting their parent planets. These irregular moons are a beautiful reminder that not all celestial bodies conform to perfect spherical symmetry. The cosmos is also filled with charmingly imperfect, yet equally fascinating smaller worlds. Their rugged, unrefined forms speak to a different kind of cosmic evolution, one where gravity's gentle hand is not strong enough to smooth out every imperfection, leaving behind a placid array of unique, unhurried shapes that add to the rich diversity of our solar system's satellites. As we gently drift through the celestial neighborhoods of our solar system, a recurring motif emerges across the surfaces of nearly all moons: the presence of countless craters. These circular depressions, varying greatly in size and depth, are common features on most moons, serving as silent, enduring evidence of billions of years of cosmic impacts. Each crater is a placid scar, a testament to a gentle, yet persistent, bombardment by asteroids, comets, and smaller meteoroids throughout the long history of the solar system. Over eons, these celestial visitors, large and small, have quietly etched their marks onto lunar landscapes, preserving a chronological record of past encounters. On worlds without active geological processes or thick atmospheres to erode or cover them, craters remain pristine, allowing scientists to patiently piece together the timeline of cosmic events. The sheer density of craters on older lunar surfaces speaks to a time when the early solar system was a more crowded place, with countless pieces of debris softly colliding and shaping the nascent worlds. These ancient impacts, though significant, are now part of the serene history of these celestial bodies, their remnants quietly enduring, inviting us to contemplate the unhurried passage of cosmic time. The presence of these gentle indentations across so many moons forms a universal language, a subtle geological dialect understood across the vast, tranquil expanse of space. Each circular basin, a quiet story of its distant past. Turning our attention specifically to our own moon, its serene surface reveals a fascinating array of features, including the graceful presence of rills. These are long, winding valleys, appearing like delicate, serpentine channels etched into the lunar face. Rilles are thought to be the remnants of ancient lava channels formed during a period of more active volcanism on the moon. Imagine, eons ago, molten rock gently flowing across the lunar surface, carving these measured paths as it slowly cooled and solidified. These unhurried rivers of lava would have created extensive networks, guiding the fiery material across vast plains before ultimately cooling and leaving behind these distinctive, often sinuous valleys. The smooth, curved contours of rills suggest a placid, unhurried flow, rather than a violent, rapid torrent. They are a quiet testament to a time when the moon's interior was warmer and more dynamic, allowing for such extensive surface activity. Today, these ancient features remain, perfectly preserved in the moon's airless, geologically quiet environment, offering a tranquil glimpse into its fiery past. The delicate beauty of these winding channels, stretching across the lunar landscape, invites a calm reflection on the subtle geological evolution of our closest celestial neighbor, a silent record of molten rivers now frozen in time. Another prominent and equally serene feature of the moon's surface is its vast, dark plains, known as Maria, a Latin word meaning seas. Early astronomers, observing these broad, smooth expanses through their telescopes, mistakenly believed them to be actual oceans of water, hence the poetic name. In reality, these Maria are colossal, dark plains of solidified ancient lava flows. Billions of years ago, immense, gentle volcanic eruptions welled up from the moon's interior, slowly filling vast impact basins with molten basaltic rock. As this lava patiently spread out and cooled, it formed flat, dark surfaces that contrast beautifully with the brighter, more heavily cratered highlands. The dark coloration is due to the chemical composition of the volcanic rock, which absorbs more sunlight than the anorthositic rocks of the highlands. These placid, solidified oceans of lava represent a significant period of lunar geological activity, transforming vast areas of the moon's face into smooth, unblemished expanses. The Maria stand as quiet, monumental records of the moon's interior dynamism, offering a tranquil visual history of its gradual cooling and solidification. Their smooth, dark surfaces are a serene backdrop to the moon's more rugged features, a testament to the powerful, yet unhurried, forces that shaped its ancient landscape, creating an elegant duality of light and shadow. The entire surface of our moon, from its towering mountains to its deepest craters, is covered in a delicate, pervasive layer known as regolith. This fine, powdery layer is composed of crushed rock and dust, a testament to billions of years of continuous, subtle, cosmic weathering. Regolith is formed by the ceaseless, gentle bombardment of the moon's surface by countless micrometeorites, tiny particles of space debris, and the erosive effects of the solar wind. Each minuscule impact, though individually imperceptible, slowly pulverizes the lunar rocks over vast stretches of time, creating a blanket of fine silken powder. This powdery material, often several yards deep, acts like a soft cushioning layer, blanketing the underlying bedrock and filling in the contours of the landscape. When astronauts walked on the moon, Their footprints left distinct impressions in this fine, ethereal dust, which remains perfectly preserved in the airless environment. The regolith offers a placid record of the Moon's interaction with its cosmic environment, a silent accumulation of dust that speaks to the unhurried processes of space erosion. This delicate, powdery blanket, gently formed over eons, adds to the serene, otherworldly beauty of the lunar landscape, a testament to the subtle, continuous forces that shape its surface. In stark contrast to the quiet, ancient surfaces of many moons, Jupiter's moon Io presents a landscape of perpetual, dynamic renewal. Its surface is constantly being reshaped by its hundreds of active volcanoes, making it a geologically very young world. Unlike our moon, where volcanic activity ceased billions of years ago, Io's interior remains intensely heated by Jupiter's powerful tidal forces, leading to ceaseless eruptions. These gentle, yet persistent, volcanic events continuously uncover older terrains. As new lava plains form and volcanic plumes deposit fresh material, older craters, mountains, and other geological features are slowly buried and erased. This constant, unhurried resurfacing means that Io's surface is perpetually fresh, rarely retaining any features for extended periods. It is a canvas being continuously repainted by its own internal fires, a placid testament to the moon's extraordinary internal dynamism. Io's geologically youthful appearance, a direct consequence of its intense volcanism, offers a unique window into the powerful, yet natural processes that can shape a moon's evolution. The quiet, continuous transformation of its surface highlights the profound influence of its giant parent planet, orchestrating a never-ending cycle of creation and renewal. This ceaseless reshaping forms a vibrant, living world in the Jovian system. Europa, another of Jupiter's Galilean moons, presents a strikingly different, yet equally compelling surface. Its smooth, icy crust is not heavily cratered like many ancient worlds, but instead is intricately crisscrossed with numerous cracks and ridges. These linear features, often extending for hundreds of miles, form complex interwoven patterns across Europa's serene surface, resembling delicate lines etched onto a pristine pane of glass. Scientists believe these cracks and ridges are direct evidence of the immense tidal forces exerted by Jupiter, which gently stretch and flex Europa's icy shell as it orbits. This continuous, unhurried flexing causes the brittle ice to fracture, creating the distinctive patterns we observe. It is also thought that some of these features might be formed by the subtle upwelling of warmer ice or even liquid water from the vast subsurface ocean beneath. As material slowly rises and refreezes, it could push up ridges or create new cracks. The smooth nature of Europa's surface, despite these extensive linear features, suggests an active, yet placid geological environment where older scars are gradually softened or erased. This intricate network of cracks and ridges offers a quiet, visual narrative of Europa's internal dynamics and its intimate relationship with its giant parent planet, a subtle testament to the continuous forces at play beneath its frozen exterior. The delicate geometry of these surface patterns hints at the hidden, liquid world below, inviting peaceful contemplation of its serene mysteries. Finally, we consider Ganymede, Jupiter's largest moon, which reveals a surface that is a magnificent mix of contrasting terrains, offering a tranquil geological tapestry. Ganymede's icy surface is elegantly divided into two distinct types of regions: ancient, dark, heavily cratered terrain, and younger, lighter, grooved regions. The dark, cratered areas are the oldest parts of the moon, densely packed with impact scars accumulated over billions of years, silent witnesses to a long history of cosmic bombardment. These regions are a placid record of Ganymede's early formation and the relentless barrage of debris in the nascent solar system. In beautiful contrast, the lighter, grooved terrains are characterized by intricate patterns of parallel ridges and valleys, forming complex systems known as sulci. These grooved regions are geologically younger and are believed to have formed through tectonic processes or cryovolcanism, where internal forces gently stretched, fractured, and resurfaced the icy crust. Perhaps warmer, slushy material slowly welled up from below, creating these distinct patterns. This striking duality of dark, ancient scars and bright, younger grooves offers a profound, yet placid, geological narrative of Ganymede's evolution. It speaks to a moon that has undergone significant internal activity, patiently reshaping its surface over immense spans of cosmic time. Ganymede's mixed terrain is a quiet testament to its enduring dynamism, a serene canvas upon which its long and unhurried history is beautifully inscribed, inviting peaceful contemplation of its varied past. Continuing our serene tour of Jupiter's grand lunar family, we encounter Callisto, another one of the colossal Galilean moons. In quiet contrast to its more geologically active siblings, Callisto is a world that appears to have remained largely unaltered since the early days of the solar system. Its surface is profoundly and extensively cratered, bearing the silent, enduring marks of countless impacts over billions of years. This dense tapestry of craters, covering almost every inch of its ancient face, serves as a pristine chronological record, a placid testament to the relentless bombardment that shaped the inner solar system. What makes Callisto particularly distinct is its remarkable lack of significant geological activity. Unlike Io with its ceaseless volcanoes, Europa with its resurfacing ice, or Ganymede with its grooved terrains, Callisto shows little sign of internal dynamism. Its interior is believed to be largely undifferentiated, meaning its rocky and icy components have not fully separated into distinct layers, suggesting a cold, dormant interior. This absence of active processes means that ancient craters are not erased or filled in, but rather remain perfectly preserved, offering a tranquil glimpse into a distant epoch. Callisto drifts through space as an ancient sentinel, a quiet, frozen archive of cosmic history, its surface a placid, unhurried chronicle of the solar system's formative years. Its unchanging face embodies a profound stillness, a testament to a world that has patiently endured, largely untouched by the profound internal forces that have reshaped its neighboring moons. The sheer number and depth of its craters tell a long, slow story of its journey through time, making it a unique and serene example of an arrested cosmic development. Shifting our focus back to Saturn's largest moon, Titan, we delve deeper into the intricate details of its captivating surface. Beneath its dense, hazy atmosphere, Titan's landscape is surprisingly diverse, featuring vast plains that stretch across immense distances, alongside majestic mountain ranges that rise subtly from the surface. These varied topographical features are not merely static structures. They bear clear evidence of liquid methane erosion, a process that subtly sculpts the moon's terrain in a manner eerily similar to how water shapes Earth. Imagine meandering channels and valleys, gracefully carved by flowing rivers of liquid methane and ethane, slowly making their way across the plains. These ethereal rivers eventually empty into vast, tranquil lakes and seas, creating shorelines that are continuously, yet imperceptibly, reshaped by the gentle lapping of hydrocarbon waves. The subtle interplay of methane rain, surface flow, and evaporation creates a complete, unhurried hydrological cycle, albeit one based on a different chemistry than Earth's. Scientists observe features like alluvial fans and deltas, quiet geological signatures that confirm the long-term work of these alien liquids. Titan's surface, with its placid plains and patient mountain ranges, is a serene canvas being continuously, gently sculpted by its unique atmospheric and liquid processes. This quiet, persistent erosion paints a picture of a dynamic, yet unhurried world, where alien weather patterns subtly transform the landscape over eons, offering a tranquil glimpse into an incredibly active, yet peaceful, extraterrestrial environment. Returning to Saturn's smaller, yet profoundly active moon, Enceladus, we find the source of its famous plumes at its south pole, a series of distinctive linear fractures known as tiger stripes. These four parallel, bluish fissures, each roughly 80 miles long, are not merely surface cracks. They are the direct gateways from which the moon's spectacular plumes of water vapor and ice particles gracefully erupt into space. These fissures are constantly, yet gently, opening and closing in response to the immense tidal stresses exerted by Saturn's gravity. As Enceladus orbits, these subtle flexings cause the tiger stripes to subtly widen and narrow, acting like cosmic valves. This measured, rhythmic movement allows material from the moon's warm, subsurface ocean to be patiently squeezed out into the vacuum of space. The plumes themselves are not violent explosions, but rather a continuous, serene outpouring of icy particles and gas, creating a diffuse, ethereal halo around the moon. The presence of these specific, active fissures provides compelling evidence for the dynamic nature of Enceladus's interior and the ongoing processes that maintain its hidden ocean. The tiger stripes are a placid testament to the moon's internal warmth and its intimate connection to the deep liquid reservoir beneath its icy crust, a quiet, continuous revelation of its hidden wonders. These distinctive features are a beautiful, unhurried display of cryovolcanic activity, silently broadcasting the moon's secrets across the vast cosmic expanse. Journeying to another of Saturn's icy companions, Mimas stands out due to a single, colossal geological feature that dominates its surface. This small moon is famous for its enormous Herschel crater, an impact basin so vast and deep that it makes Mimas strikingly resemble the Death Star from science fiction. The crater itself is approximately 81 miles across, almost 1/3 of the moon's entire diameter. Its rim rises several miles above the surrounding terrain, and a prominent central peak gently ascends from its floor. This monumental impact, which must have occurred eons ago, was a formative event that left an indelible mark on Mimas, subtly reshaping its structure without tearing it apart. The sheer scale of Herschel crater suggests an impactor of considerable size, yet Mimas gracefully absorbed the energy, bearing a quiet, permanent scar. The impact caused subtle fracturing on the moon's opposite side, evidence of the immense forces at play. Despite its dramatic appearance, Mimas continues its placid orbit around Saturn, its immense crater a silent, enduring testament to a powerful, yet ancient, cosmic encounter. This striking resemblance to a fictional spacecraft's weapon is a fascinating visual quirk, a gentle reminder of the unexpected forms celestial bodies can take, shaped by their unhurried history of cosmic events. The crater's immense presence is a profound, yet tranquil feature that defines Mimas, a silent marvel in Saturn's diverse family of moons. Venturing into the distant, dim light of the Uranian system, we encounter Umbriel, a moon of Uranus that holds the distinction of being one of the darkest moons in the solar system. Its surface reflects very little sunlight, giving it a somber, muted appearance compared to the brighter, more reflective icy worlds around it. This enigmatic darkness is believed to be due to a surface composition rich in carbonaceous material, possibly mixed with primordial organic compounds. Over eons, space weathering, the subtle effects of solar radiation and micrometeorite impacts, may have also contributed to the darkening of its icy crust, creating a pervasive, almost uniform, dark hue. Umbriel's surface is heavily cratered, indicating a very ancient and largely inactive geological history, much like Jupiter's Callisto. The lack of bright features or evidence of recent resurfacing further contributes to its overall dimness. It drifts through space as a quiet, enigmatic sphere, its dark surface absorbing much of the faint sunlight that reaches it, presenting a placid, almost melancholic presence in the Uranian system. This profound darkness is a subtle testament to its unique composition and long, unhurried exposure to the cosmic environment. Umbriel's serene, somber appearance invites a quiet contemplation of the varied albedos and surface histories that define the diverse collection of moons in our solar system, a tranquil, dark jewel amidst its brighter companions. Adjacent to Umbriel, Titania, the largest moon of Uranus, presents a more geologically active, yet equally serene, history. Its surface is marked by immense canyons and fault lines, subtle linear scars that stretch across vast distances. These Grand Canyons, often hundreds of miles long and several miles deep, are believed to be the result of past tectonic activity. Scientists propose that as Titania's interior slowly cooled and expanded or contracted, its icy crust gently fractured and shifted, creating these profound geological features. This process of expansion or contraction, occurring over immense stretches of cosmic time, would have slowly pulled the crust apart, forming vast rifts or pushed sections together, creating subtle compressional features. The unhurried movements of its icy shell created a network of these linear features, a placid record of its internal evolution. While Titania is not volcanically active in the same way as Io or Enceladus, these canyons and fault lines provide clear evidence of a dynamic yet measured geological past. Titania's surface, with its elegant network of deep fissures, offers a tranquil window into the gentle, long-term tectonic processes that can shape icy worlds in the distant outer solar system. These grand, linear features are a quiet testament to the enduring, subtle forces that patiently sculpt the surfaces of large moons, revealing a history of gradual, internal transformation. Finally, we turn our gaze to Oberon, another large moon of Uranus, which, like Callisto and Umbriel, displays a heavily cratered surface. This dense covering of impact craters, some of them quite substantial, indicates that Oberon has a very ancient surface, largely preserving the record of impacts from the early solar system. Its face is a placid tapestry of ancient scars, each crater a silent witness to countless celestial collisions over billions of years. Amidst this cratered expanse, Oberon also features a few large mountains, which may be the central peaks of exceptionally old and eroded impact basins, or perhaps subtle uplifts from very early tectonic activity. These gentle mountainous features rise serenely from the cratered plains, adding a subtle vertical dimension to its otherwise flat, ancient landscape. Unlike the more dynamic Titania, with its extensive canyon systems, Oberon shows little evidence of recent large-scale geological activity, suggesting a cold, relatively inert interior. It drifts through space as a quiet, venerable world, its surface a testament to a long and unhurried history of cosmic bombardment and patient preservation. Oberon's ancient cratered face and its few subtle mountains offer a tranquil glimpse into the long-term evolution of icy moons that have remained largely undisturbed since their formation, a placid record of cosmic time etched in ice and rock, inviting peaceful contemplation of its enduring stillness. As we journey further into the dim, Nereid, a moon of Neptune, which holds a truly unique distinction. It possesses the most eccentric orbit of any moon in our entire solar system. An eccentric orbit means that Nereid's path around Neptune is not a gentle, nearly circular curve, but a highly elongated ellipse. This results in immense variations in its distance from the giant planet. At its closest approach, Nereid may come within less than 900,000 miles of Neptune, while at its farthest point, it can drift more than 6 million miles away. This profound fluctuation in distance creates a slow, unhurried, yet dramatically unpredictable journey. Scientists believe that Nereid's extraordinarily eccentric orbit is a subtle testament to a tumultuous past, likely a consequence of Neptune's capture of its massive moon Triton. The immense gravitational forces unleashed during Triton's slow, gentle settling into its retrograde orbit would have subtly disturbed Nereid's original path, stretching it into its current, elongated form. Nereid thus drifts through space as a solitary, placid wanderer, its highly elliptical route a silent record of ancient cosmic events. Its measured, wide-ranging path offers a tranquil glimpse into the lasting, subtle effects of gravitational reshuffling in the outer solar system, a testament to the enduring, unhurried consequences of planetary evolution. This moon's unique orbital characteristic is a beautiful, quiet anomaly, highlighting the diverse and sometimes surprising dynamics that can emerge in the celestial dance of planets and their companions. The long, slow sweep of Nereid across the Neptunian sky is a constant, unhurried reminder of the subtle forces that shape the most distant corners of our cosmic neighborhood. Beyond the external influences that shape a moon's path, the internal warmth of many moons is profoundly affected by the gentle interplay of tidal forces between a moon and its parent planet. This subtle, yet powerful, gravitational interaction can cause significant internal heating within the moon. As a moon orbits its planet, the planet's immense gravity subtly stretches and compresses the moon's interior in a rhythmic, unhurried fashion. This continuous flexing, a gentle kneading of the moon's rocky or icy layers, generates internal friction. This friction, in turn, converts gravitational energy into thermal energy, slowly heating the moon's core and mantle. We have seen this phenomenon at work on Io, where Jupiter's powerful pull fuels its volcanoes, and on Europa and Enceladus, where tidal heating maintains their vast subsurface oceans. This process, persistent deformation, a natural and placid mechanism that keeps these worlds internally active. The subtle, ceaseless tug and release of gravity provide a continuous, unhurried source of warmth, allowing for geological processes or even the maintenance of liquid water in environments far from the sun's direct heat. This internal warmth, patiently generated over eons, plays a crucial role in shaping a moon's evolution, often leading to dynamic yet serene surface features and the potential for sustaining life. The quiet hum of tidal heating is a constant, imperceptible force, silently shaping worlds from within. Within complex multi-moon systems, a fascinating and elegant phenomenon known as orbital resonance often occurs, where moons exert regular gravitational pulls on each other, frequently leading to the stabilization of their orbits. Orbital resonance describes a situation where the orbital periods of two or more moons are in a simple, whole number ratio, such as 1:2 or 1:4. This synchronized timing means that the moons repeatedly align in specific configurations, allowing their gentle gravitational interactions to occur at predictable intervals. Instead of causing chaos or collisions, these regular gravitational nudges often reinforce each other in a way that helps to stabilize the moon's orbits, preventing them from drifting too far or too close to their planet or to each other. For example, Jupiter's Galilean moons, Io, Europa, and Ganymede are locked in a 1:2:4 orbital resonance, a delicate, unhurried dance that has maintained their stability for billions of years. This harmonious interplay is a beautiful example of nature's elegant solutions for maintaining order within complex systems. Orbital resonance creates a placid, rhythmic ballet, ensuring the long-term stability and coexistence of multiple satellites, a silent testament to the intricate precision of celestial mechanics. The subtle, synchronized gravitational pulls create an enduring cosmic harmony, a patient and measured choreography that prevents disruption and ensures a peaceful, continuous journey for each moon. Our own moon, Earth's familiar companion, plays a far more profound role than merely influencing our tides. Its gravity also stabilizes Earth's axial tilt, leading to a more stable climate. Earth's axis of rotation is currently tilted at approximately 23.5 degrees relative to its orbital plane around the Sun. This tilt is responsible for our planet's seasons, as different parts of Earth receive more direct sunlight at various times of the year. However, without the Moon's substantial gravitational presence, Earth's axial tilt would not be nearly as stable. Over geological timescales, the gravitational influences of other planets, particularly Jupiter, would cause Earth's axis to wobble dramatically, shifting its tilt by many tens of degrees. These wild, unhurried oscillations in axial tilt would lead to extreme and unpredictable climate variations, making it profoundly challenging for complex life to develop and persist. The moon acts as a steadying hand, its gentle gravitational pull patiently dampening these potential wobbles, keeping Earth's tilt relatively constant. This profound yet subtle lunar influence has provided our planet with billions of years of a remarkably stable climate, evolution of life. The moon's silent, stabilizing presence in our sky is a placid testament to its integral role in making Earth a habitable world, a beautiful example of cosmic interconnectedness that often goes unnoticed. The gentle, persistent tug of our lunar partner ensures a continuous, measured balance for our planet, fostering a tranquil environment for life's unfolding story. Within the magnificent, shimmering expanse of planetary rings, small, dedicated celestial bodies known as shepherd moons perform a vital yet subtle role. These moons, typically tiny and often irregularly shaped, act as quiet sculptors, using their gentle gravitational influence to clear paths for material within the planetary rings. As they orbit within or near the edges of a ring, their gravity subtly nudges and guides the countless particles of ice and dust that constitute the rings. The inner shepherd moons gently push ring particles outward, while outer shepherd moons subtly pull them inward. This delicate gravitational interaction effectively clears out distinct gaps and maintains the remarkably sharp edges of the rings. Without these patient guardians, the ring material would likely spread out and diffuse, losing its intricate structure and defined boundaries. They are like serene cosmic herders, patiently corralling billions of tiny particles, ensuring the enduring beauty and delicate organization of the ring system. This continuous, unhurried sculpting is shepherd placid spectacle for all to behold. Their quiet work is a testament to the intricate, measured precision of celestial mechanics, shaping cosmic artistry with a delicate touch. The delicate balance of gravitational forces also defines a critical boundary around any celestial body, the Roche limit. This is the specific distance within which a celestial body, held together only by its own gravity, will gently break apart due to the overwhelming tidal forces exerted by a larger, more massive object. If a moon or other celestial body, without significant internal cohesive strength, ventures inside this invisible boundary, the gravitational pull from the primary body on the moon's near side becomes significantly stronger than on its far side. This differential pull creates immense tidal stresses, which patiently overcome the moon's own self-gravity, causing it to slowly disintegrate. The process is not a violent explosion, but a gradual, unhurried fragmentation as the moon's material gently disperses, often forming a new ring system around the larger planet. This is the likely fate awaiting Mars's moon Phobos, which is slowly spiraling inward towards the red planet. The Roche limit offers a placid explanation for the formation of many planetary rings, where moons or asteroids that strayed too close were gently torn apart, their fragments then spreading into a beautiful, diffuse disk. It is a silent, fundamental principle of celestial mechanics, defining the delicate balance between gravitational cohesion and tidal disruption, shaping the evolution of moons and rings across the cosmos. This boundary is a quiet, yet powerful testament to the subtle, yet irresistible forces of gravity, patiently dictating the ultimate fate of celestial bodies. Finally, when we observe planets with many moons, such as Jupiter or Saturn, we invariably find that they possess complex orbital systems characterized by a multitude of intricate interactions. The presence of numerous satellites orbiting a massive parent planet creates a dense gravitational environment where each moon's movement is subtly influenced by the others. These interactions are not chaotic, but rather a sophisticated, unhurried dance of gravitational pulls and nudges. Moons can enter into orbital resonances, as we discussed, or experience subtle perturbations that gently alter their paths over long periods. The gravitational forces between these many companions can lead to phenomena like tidal heating, orbital migration, and even the occasional gentle exchange of material. Understanding these complex systems requires patient observation and sophisticated modeling, as the subtle interplay of gravity dictates the long-term stability and evolution of the entire lunar family. This intricate web of gravitational relationships creates a dynamic yet placid cosmic environment, where each moon plays a unique role in the overall harmony of the system. The sheer number of moons around these gas giants transforms their immediate surroundings into a miniature solar system, gravity to organize and orchestrate a continuous, unhurried celestial ballet. The delicate balance and constant, imperceptible adjustments within these populous lunar families reveal the profound beauty of cosmic complexity, a serene and intricate tapestry woven by gravitational threads. As we continue our exploration of lunar dynamics, a common and elegant characteristic observed among many moons is synchronous rotation. This fascinating phenomenon means that a moon's rotation period perfectly matches its orbital period around its parent planet. The most familiar example, of course, is our own moon, which always presents the same face to Earth. This unstable the moon and its planet over billions of years. The planet's gravity creates subtle tidal bulges on the moon, and these bulges exert a gentle torque, gradually slowing down the moon's rotation until it reaches a point where one side is perpetually pulled towards the parent body. Once achieved, this tidally locked state is remarkably stable, maintaining a placid, synchronized dance. This unhurried process ensures a consistent, predictable relationship, where the moon's rotation is perfectly attuned to its orbital journey. Many of the large inner moons of the gas giants, such as Jupiter's Io and Europa and Saturn's Titan, are also in synchronous rotation. This elegant celestial choreography offers a quiet testament to the enduring power of tidal forces, patiently shaping the rotational dynamics of satellites across the cosmos. The constant, unchanging view of one lunar face from its parent planet is a serene reminder of this profound gravitational lock, a beautiful, measured rhythm in the vastness of space. Our own moon, in its serene and constant presence, exerts a subtle yet profound influence on our planet, gently affecting the very rhythm of our days. The Earth's moon influences the length of our day, gradually slowing Earth's rotation. This phenomenon, as we have touched upon, between the Earth and the moon. The moon's gravity creates bulges in Earth's oceans. And because Earth rotates much faster than the moon orbits, these tidal bulges are carried slightly ahead of the moon's direct line of pull. The moon's gravity then subtly tugs back on these leading bulges, slowing down Earth's rotation, much like a gentle brake. In return, this interaction gradually spirals farther away from Earth. This is a continuous, unhurried transfer of angular momentum, a placid exchange of energy between our planet and its satellite. Over billions of years, this slow deceleration has significantly lengthened Earth's day, which was much shorter in the distant past. This ongoing, imperceptible change bodies a quiet, patient reshaping of our planet's fundamental rhythms. The moon's gentle, persistent pull is a silent clock, slowly altering the passage of time on Earth in our immediate cosmic neighborhood. Returning to Mars, its innermost moon, Phobos, demonstrates an extraordinarily close and rapid orbital relationship with its parent planet. Phobos orbits so closely to Mars that it completes 3 orbits per Martian day. This means that from the surface of Mars, an observer would witness Phobos rising and setting multiple times during a single Martian day, a truly unique and swift celestial ballet. Its incredibly tight orbit, just a few thousand miles above the Martian surface, makes it one of the fastest orbiting moons in the solar system, relative to its planet's rotation. This rapid orbital period is a direct consequence of its close proximity to Mars and the strong gravitational pull exerted by the red planet. The quick, unhurried passage of Phobos across the Martian sky highlights its unique position. Constantly under the intense tidal influence of its parent, This close gravitational embrace is also why Phobos is gradually spiraling inward, destined for a gentle disintegration or impact with Mars in the distant future. The serene, swift journey of Phobos is a placid reminder of the diverse orbital dynamics found within our solar system, a testament to the powerful, yet subtle, gravitational forces that shape the fates of close-in moons. Its rapid, continuous circuits are a quiet, measured dance, offering a fleeting glimpse into a unique celestial rhythm. Among the myriad moons of our solar system, the 4 Galilean moons of Jupiter, Io, Europa, Ganymede, and Callisto, stand out as truly exceptional. These colossal satellites are not only among the largest moons in our solar system, but are also the most extensively studied. Each of these worlds is a unique marvel, offering a diverse array of geological phenomena and potential for discovery. Io, with its ceaseless volcanism, reveals the extreme effects of tidal heating. Europa, with its subsurface ocean, hints at the potential for life beyond Earth. Ganymede, the largest moon of all, boasts its own magnetic field and a complex grooved terrain. Callisto, ancient and heavily cratered, serves as a serene archive of the early solar system. Their substantial sizes, ranging from roughly the size of Earth's moon to larger than the planet Mercury, make them worlds in their own right, each with its own intricate history and ongoing processes. The quiet, unhurried observations of these 4 celestial giants have profoundly expanded our understanding of planetary science, revealing the incredible diversity and dynamism that can exist within a single planetary system. These Galilean moons drift through space as placid titans, each endless wonders of our cosmos, patiently revealing their secrets through continuous scientific inquiry. The very discovery of these magnificent Jovian companions marks a pivotal moment in astronomical history. The 4 major moons of Jupiter, now famously known as the Galilean moons, were discovered by the pioneering astronomer Galileo Galilei in 1610. Using his newly refined telescope, Galileo turned his gaze towards Jupiter and observed 4 faint stars subtly shifting their positions around the giant planet over successive nights. His meticulous, unhurried observations led him to the profound realization that these celestial bodies were not fixed stars, but rather satellites orbiting Jupiter. This discovery provided compelling evidence against the long-held geocentric model of the universe, which placed Earth at the center of all celestial motion. Instead, it offered tangible proof that not everything revolved around our planet, lending powerful support to the heliocentric model proposed by Copernicus. Galileo's serene, patient observations fundamentally transformed our understanding of the cosmos, ushering in a new era of astronomical discovery. The quiet revelation of these 4 distant worlds marked a profound shift in human perspective, demonstrating the immense power of observation and careful reasoning. Their discovery, a placid turning point in scientific thought, continues to inspire awe and wonder, reminding us of the subtle beauty of uncovering cosmic truths through patient inquiry. Beyond the well-ordered inner moon systems, many irregular moons grace the distant reaches of our solar system, orbiting far from their parent planet, and often exhibiting unique orbital characteristics. These moons, typically small and irregularly shaped, gently drawn into the gravitational embrace of the gas giants. What makes them irregular is their often distant orbits, which are frequently highly inclined relative to the planet's equatorial plane. This means they circle their planet at a significant angle, sometimes even orbiting in a retrograde direction, opposite to the planet's rotation. These peculiar orbital paths are subtle hallmarks of their captured origins, reflecting a history of gentle gravitational nudges and interactions that brought them into their current configurations. They drift through space as placid wanderers, their long, unhurried journeys taking them far from the planet's immediate vicinity. The study of these irregular moons provides valuable insights into the dynamics of celestial capture and the distribution of small bodies in the outer solar system. Their distant, often tilted orbits offer a tranquil glimpse into the subtle, adding a layer of quiet complexity to the vast families of satellites. Each of these distant, irregularly shaped companions, gravity in the remote corners of our solar system. The long, unhurried lives of moons are not eternal, and the subtle forces of gravity ensure that some moons may eventually fall into their parent planet or be ejected from the system. These fates are not violent or dramatic, but rather represent the patient, long-term outcomes of gravitational interactions. A moon slowly spiraling inward, like Mars's Phobos, may eventually cross its planet's Roche limit, gently breaking apart to form a temporary ring system, or experience a soft, unhurried impact with the planet's surface. This gentle descent is a consequence of persistent tidal forces slowly transferring orbital energy. Conversely, moons that orbit very far from their parent planet, particularly irregular, captured moons, may experience subtle gravitational nudges from other celestial bodies, or even the distant sun. These gentle perturbations can, over immense stretches of cosmic time, slowly increase the moon's orbital energy, eventually causing it to be subtly ejected from the planet's gravitational embrace altogether. Such a moon would then become an independent wanderer once more, embarking on a new, solitary journey through interstellar space. These cosmic destinies are part of the placid, continuous evolution of planetary systems, gravity to reshape and redistribute celestial bodies. The quiet, unhurried dissolution or departure of a moon is a natural, non-dramatic process, illustrating the impermanence of celestial bonds and the constant, measured flux of the cosmos. It is a serene universe, are subject to slow, graceful change over eons. As we turn our gaze back to our own familiar night sky, the moon presents a continuously unfolding spectacle of light and shadow. Its phases. The moon's phases are caused by the changing angles at which we view its illuminated surface from Earth. The moon itself does not produce its own light, it gently reflects sunlight. As the moon patiently orbits Earth, the portion of its surface that is lit by the sun changes from our perspective. When the moon is between Earth and the sun, its sunlit side faces away from us, appearing as a new moon, a dark, serene silhouette against the stars. As it slowly moves around Earth, more of its illuminated face gradually becomes visible, transitioning through crescent, quarter, and gibbous phases. When the moon is on the opposite side of Earth from the sun, its entire sunlit side faces us, revealing a full moon, a radiant, placid orb. This continuous, unhurried cycle, taking approximately 29.5 days to complete, is a beautiful and predictable celestial dance. The moon's gentle, rhythmic progression through its phases has guided human calendars, inspired countless stories, and served as a constant, comforting presence in our skies for millennia. This subtle interplay of light, shadow, and orbital motion creates an elegant, ever-changing tableau, a silent testament to the simple yet profound mechanics of our Earth-Moon system. The serene unfolding of these phases invites quiet contemplation, connecting us to the larger cosmic rhythms with each passing night. Our understanding of these distant lunar worlds has been profoundly deepened by the dedicated efforts of numerous space missions. Over the decades, robotic explorers have embarked on long, unhurried journeys across the solar system, patiently revealing the intricate details of moons around distant planets. Missions like Cassini, which orbited Saturn for over 13 years, provided breathtaking close-up views and invaluable data on its extensive moon system, including the geysers of Enceladus and the hazy atmosphere of Titan. Similarly, the Galileo mission, orbiting Jupiter, meticulously studied its 4 colossal Galilean moons, uncovering their diverse geological features and hinting at subsurface oceans. These spacecraft, designed with meticulous care, have quietly traveled for years, sometimes decades, across immense cosmic distances, patiently collecting data and transmitting it back to Earth. Their serene voyages have transformed our understanding of these satellites from mere points of light into complex, dynamic worlds. The persistent work of these robotic explorers, silently gathering knowledge in the vacuum of space, is a testament to humanity's unhurried quest for understanding the cosmos. Each mission, a placid journey of discovery, has contributed to a rich tapestry of knowledge, allowing us to virtually drift among these celestial companions and unravel their long-held secrets. Among the pioneering robotic explorers, the Voyager spacecraft stand as monumental achievements, having provided humanity with the first close-up images of many outer planet moons. Launched in the late 1970s, Voyager 1 and Voyager 2 embarked on grand tours of the outer solar system, patiently flying past Jupiter, Saturn, Uranus, and Neptune. As they gracefully approached these gas giants, their cameras and instruments captured unprecedented views of their diverse lunar families. Before Voyager, many of these moons were little more than indistinct points of light, their surfaces and features unknown. Voyager's unhurried flybys revealed the volcanic fury of Io, the icy smoothness of Europa, the mysterious tiger stripes of Enceladus, and the jumbled terrain of Miranda, among countless other wonders. These iconic images, transmitted across billions of miles, transformed our perception of these distant worlds, revealing them as active, complex, and beautiful. The Voyager missions were a serene testament to human ingenuity, pushing the boundaries of exploration and offering humanity its first intimate glimpse of these remote celestial companions. Their quiet, continuous journey beyond the solar system carries these placid images and scientific data, a lasting legacy that continues to inspire awe and wonder about the vastness and diversity of the cosmos. Looking towards the future, the promise of even more profound discoveries beckons, with future missions specifically planned to search for signs of life in the subsurface oceans of Europa and Enceladus. Building upon the tantalizing evidence gathered by past missions, space agencies are now meticulously designing spacecraft to directly investigate these hidden watery worlds. The Europa Clipper mission, for instance, will perform numerous close flybys of Europa, patiently gathering data on its ice shell, ocean, and potential plumes, seeking to confirm habitability. Similarly, concepts for missions to Enceladus aim to fly directly through its plumes, collecting samples of the ejected material to search for biosignatures, subtle chemical indicators of life. These ambitious missions represent the next serene step in humanity's quest to understand the prevalence of life in the universe. The careful, unhurried design and execution of these endeavors underscore the scientific community's deep commitment to exploring these placid, hidden oceans. The quiet anticipation of potentially discovering microbial life thriving in these distant, dark waters fuels a profound sense of wonder, offering a tranquil glimpse into the possibilities of life beyond Earth and inspiring us to patiently continue our cosmic search. Among the many intriguing moons, Titan, Saturn's largest satellite, is considered a prime target for future human exploration due to its unique atmosphere and surface liquids. Unlike the airless, stark landscapes of most moons, Titan offers a world enveloped in a thick, nitrogen-rich atmosphere, providing a natural shield from radiation. Beneath this hazy veil lie vast, tranquil lakes and seas of liquid methane and ethane, forming a serene and alien hydrological cycle. For future human explorers, this atmosphere could potentially allow for flight with relatively simple aircraft, and the liquid bodies offer a source of unique chemistry and potential resources. The idea of future missions involving serene, unhurried exploration by human crews, perhaps sailing across methane seas or flying through its dense atmosphere, sparks the imagination. Titan's rich and complex environment, while cold and alien, presents a challenging yet profoundly rewarding destination for understanding planetary processes and the potential for different forms of life. Its unique blend of atmospheric protection and surface liquids makes it a placid frontier for future endeavors. A quiet, inviting world for humanity's next great cosmic adventure. The slow, patient development of technology will one day allow for this tranquil journey to unfold, revealing even more of Titan's unhurried mysteries. The exploration of moons, whether by robotic probes or through future human endeavors, provides invaluable insights into the early history and formation of the solar system. Each moon, with its unique composition, surface features, and orbital characteristics, serves as a placid time capsule, preserving clues about the conditions that prevailed billions of years ago. By studying the cratered surfaces of ancient moons like Callisto, scientists can patiently reconstruct the intensity of early bombardment periods. Analyzing the composition of moons helps us understand the distribution of materials in the early solar nebula and how planets accreted. The diverse origins of moons, through co-accretion, capture, or giant impacts, offer different perspectives on the dynamic processes that shaped the nascent solar system. These quiet, unhurried investigations allow astronomers to piece together a comprehensive narrative of cosmic evolution, from the swirling dust clouds that formed our sun and planets to the intricate orbital ballet of their satellites. Exploring moons is like reading chapters from an ancient, serene cosmic book, each page revealing more about the foundational moments of our celestial neighborhood. This patient accumulation of knowledge, derived from the silent observation of these distant worlds, provides a tranquil, profound understanding of our origins and the unhurried processes that led to the formation of everything we see today. As humanity looks beyond Earth, the moons of our solar system present themselves not only as objects of scientific curiosity, but also as potential reservoirs of vital resources for future space exploration. Some moons may contain valuable resources, like water ice, which would be crucial for sustaining long-duration missions and establishing permanent outposts. Water ice, abundant on many icy moons of the outer solar system, and even potentially in permanently shadowed craters on our own moon, can be gently harvested and processed. It can be melted for drinking water, split into hydrogen and oxygen for rocket fuel, or used for breathable air. The subtle presence of these frozen reserves transforms these distant worlds into potential cosmic fueling stations and supply depots, quietly supporting humanity's expansion into the solar system. The serene extraction of these resources would represent a significant step in making space travel more sustainable and less reliant on costly launches from Earth. This placid potential for resource utilization underscores the practical importance of studying moons, revealing their unhurried role in enabling humanity's future in space. The gentle availability of water ice, a silent, frozen treasure, could patiently unlock new frontiers of exploration and settlement, making the vastness of space a more accessible and tranquil realm for future generations. Beyond their practical applications, the systematic study of moons provides profound insights into the fundamental processes of planetary formation. Each moon, regardless of its size or composition, offers a unique data point in the grand narrative of how celestial bodies come into being. By observing moons that formed through co-accretion, capture, or giant impact, scientists can patiently refine their models of how planets gather their material and how satellite systems evolve. The chemical makeup of a moon can reveal the conditions in the protoplanetary disk from which it emerged, while its orbital characteristics can speak to the gravitational dynamics of its early history. For instance, the presence of captured asteroids as moons around gas giants helps us understand the population of small bodies in the early solar system and the efficiency of gravitational capture. The intricate details of tidal heating on moons like Io provide a placid window into the internal energy budgets of celestial bodies. This continuous, unhurried investigation of moons allows astronomers to piece together a comprehensive, elegant picture of how our solar system, and indeed other planetary systems, patiently assembled themselves over billions of years. The quiet study of these diverse companions enriches our understanding of the subtle, yet powerful, forces that sculpt planets and their retinues, revealing the underlying principles of cosmic architecture. The sheer diversity of environments found across the moons of our solar system is truly remarkable. Moons offer environments ranging from geologically active to ancient and dormant, each a unique laboratory for understanding planetary processes. Io's ceaseless volcanism, fueled by Jupiter's tidal forces, represents an extreme example of geological activity, its surface constantly remade by gentle flows of lava. In serene contrast, Callisto's ancient, heavily cratered surface stands as a placid testament to a dormant interior, preserving a pristine record of the early solar system. Enceladus and Europa, with their hidden subsurface oceans and active plumes, offer dynamic, icy worlds with the potential for life. Titan, with its dense atmosphere and liquid methane seas, presents a world of alien weather and unique chemistry. This vast spectrum of lunar environments underscores the varied pathways of planetary evolution, patiently shaped by factors such as size, composition, distance from the parent planet, and the intensity of tidal heating. The quiet exploration of these diverse worlds allows scientists to compare and contrast different geological histories, revealing the subtle interplay of forces that dictate a moon's fate. This placid array of lunar landscapes, from fiery infernos to frozen archives, offers a tranquil glimpse into the boundless creativity of the cosmos, where each moon tells its own unhurried story of enduring transformation or profound stillness. The discovery of new moons is an ongoing process, a continuous, unhurried endeavor made possible as observational technology improves. Even after centuries of astronomical observation, our solar system continues to reveal its hidden companions. Advanced telescopes, both on Earth and in space, coupled with sophisticated image processing techniques, allow astronomers to patiently detect fainter, smaller, and more distant moons that were previously invisible. The gas giants, fertile grounds for these new discoveries, as they continue to subtly capture passing asteroids and comets. These newly found moons are often tiny, perhaps only a few miles across, and orbit far from their parent planet, making them challenging to spot. Each new discovery adds another piece to the intricate puzzle of solar system formation and evolution, enriching our understanding of orbital dynamics and celestial capture. This continuous, placid unveiling of previously unseen companions is a testament to the enduring human quest for knowledge and the ever-improving capabilities of our scientific instruments. The quiet addition of each new moon to our cosmic catalogue underscores the vastness of what remains to be discovered, inviting us to patiently continue our serene exploration of the universe's hidden depths. Looking beyond our own solar system, scientists also expect that distant exoplanets are also expected to have their own exomoons. Given the prevalence of moons around planets in our solar system, the formation processes that create moons, whether through co-accretion, capture, or giant impacts, are universal mechanisms expected to operate around planets orbiting other stars. While currently challenging to detect directly, the theoretical presence of exomoons opens up a vast new realm of possibilities. These distant celestial companions could be incredibly diverse, ranging from icy worlds similar to Europa to gas-shrouded satellites like Titan, or even rocky bodies unlike anything in our own system. The quiet expectation of their existence fuels a profound sense of wonder, inviting us to contemplate the countless unseen worlds that patiently orbit planets across the galaxy. The subtle gravitational influence of exomoons on their host exoplanets could provide indirect clues to their presence, a quiet whisper across light years. This placid yet profound anticipation of exomoons expands our cosmic perspective, reminding us of the boundless variety of celestial configurations that patiently await discovery in the vastness of the universe. The search for these elusive exomoons is challenging, but it holds the profound promise of discovering new types of celestial bodies and unlocking deeper secrets of planetary formation. Directly observing an exomoon is incredibly difficult due to their small size and the overwhelming brightness of their host stars and planets. However, astronomers are patiently developing innovative techniques to detect them. These methods include looking for subtle variations in the timing of an exoplanet's transit across its star, or searching for tiny, additional dips in starlight that might indicate the presence of an accompanying moon. The successful detection of exomoons would not only confirm their existence, but would also allow scientists to study their characteristics, such as size, mass, and orbital period, providing invaluable data on how moons form and evolve in different stellar environments. This placid, unhurried quest for distant satellites could reveal entirely new classes of celestial objects, expanding our understanding of planetary systems beyond the familiar confines of our own. The quiet pursuit of these challenging observations represents a frontier of astronomical discovery, promising a tranquil unveiling of the universe's hidden complexities and further enriching our cosmic tapestry with new and wondrous worlds. Finally, as we observe the subtle nuances of these celestial companions, moons can sometimes be distinguished by their unique colors or spectral signatures. The surface composition of a moon, influenced by its formation, geological activity, and exposure to space weathering, can impart distinct hues or patterns in the light it reflects. For instance, Io's vibrant multicolored surface is dominated by sulfur compounds, giving it a striking yellow, orange, and red appearance. Triton's surface shows subtle pinkish and reddish tints from nitrogen ice and tholins. Even the two-tone appearance of Iapetus is a dramatic example of color differentiation. Spectral signatures, which are the unique patterns of light absorption and reflection across different wavelengths, provide even more detailed information. By patiently analyzing the light reflected or emitted by a moon, scientists can identify the specific elements and compounds present on its surface, such as water ice, silicates, or organic molecules. These subtle distinctions in color and spectral data act as quiet fingerprints, allowing astronomers to remotely study the composition and history of distant moons. This placid analysis of light offers a tranquil window into the diverse chemistries and geological processes that shape these celestial bodies. The gentle variations in their reflected light create a beautiful, unhurried palette across the cosmic canvas, revealing the unique identity of each moon in the vast, serene expanse of our solar system. As we continue to observe the celestial ballet around us, a remarkable truth emerges. The total number of moons in our solar system, including those of dwarf planets and asteroids, is constantly being updated. Our cosmic neighborhood is far more populous than once imagined, and the quiet pursuit of astronomical discovery continuously reveals new, previously unseen companions. This ongoing process of updating the lunar census is a testament to the persistent refinement of observational technology. Powerful ground-based telescopes, equipped with adaptive optics, and sophisticated space-based observatories like the Hubble Space Telescope, patiently peer into the dim, distant reaches of space, seeking out faint, moving points of light. These instruments, combined with advanced image processing techniques, allow astronomers to detect moons that are incredibly small, often just a few miles across, or that orbit far from their parent planets, making them challenging to spot. The gas giants, with their immense gravitational spheres of influence, are particularly patiently adding them to their already extensive retinues. Each new discovery adds another delicate, the subtle processes of these newly found, often irregularly shaped, objects tell silent tales of distant journeys before their gentle adoption into a new planetary family. Their faint light, barely discernible against the cosmic backdrop, speaks to the unhurried precision of astronomical observation, slowly painting a more complete picture of the myriad worlds that share our sun's embrace. The sheer volume of these discoveries reflects a profound, yet gentle complexity, where even the smallest celestial wanderers find their place in the grand, unhurried dance of the solar system. The quiet, persistent efforts of scientists ensure that our understanding of these celestial families is always growing, always becoming more nuanced and complete, a continuous narrative of discovery that unfolds with patient grace. Beyond the sheer numbers and diversity of moons, the presence of a large moon, like Earth's, can be profoundly crucial for the development of life by stabilizing a planet's climate. Our own moon, Earth's steadfast and substantial companion, acts as a silent guardian, gently regulating our planet's axial tilt. Earth's axis, the imaginary line around which it rotates, is currently tilted at an angle of the elegant architect of our planet's seasons, ensuring a gentle variation in sunlight across the year, which is vital for many ecosystems. However, without the moon's considerable remain so stable, over immense geological timescales, the subtle gravitational influences of other planets, particularly the colossal, these unhurried yet profound oscillations in axial tilt could shift by many tens of degrees, leading to extreme and unpredictable climate variations. Imagine long periods of intense heat followed by epochs of deep cold, rendering vast regions of the planet uninhabitable. Such chaotic climate instability would make it incredibly, as evolving organisms would struggle to adapt to such rapid and severe environmental shifts, remarkably relatively complex. It is a quiet, continuous act of cosmic stewardship, ensuring a temperate environment for life's intricate, unhurried unfolding, where life can patiently take root and flourish over eons. This subtle, yet powerful gravitational relationship is a cornerstone of Earth's habitability, a silent, enduring bond that underpins the very possibility of life as we know it, making our moon not just a celestial body, but a profound and gentle partner in our planet's story. Journeying back to the magnificent system of Saturn, we encounter Phoebe, a moon whose characteristics tell a fascinating story of capture and subtle influence on its parent planet's rings. Phoebe, unlike many of Saturn's inner moons, is distinctly dark, irregularly shaped, and orbits at a considerable distance from the planet, taking over 550 days to complete a single, unhurried circuit. What is particularly striking about Phoebe is its retrograde orbit. It moves around Saturn in the direction opposite to the rotation of the planet and most of its other moons. These unusual characteristics, its dark, non-spherical form, distant orbit, and backward motion, strongly suggest that Phoebe is not a moon that formed alongside Saturn. Instead, scientists believe it is a captured object, likely a primordial asteroid or a Kuiper Belt object that was gently drawn into Saturn's gravitational embrace billions of years ago. Its surface is heavily cratered, a placid record of its long, independent journey through the outer solar system before its quiet adoption. Furthermore, Phoebe plays a unique and subtle role in contributing material to Saturn's distant, diffuse E-ring. As Phoebe patiently orbits, it is gently bombarded by micrometeorites. These tiny impacts subtly dislodge dust and ice particles from its surface, which then slowly spread out into space, forming a tenuous, almost imperceptible ring of material that extends far beyond Saturn's main ring system. This continuous, unhurried shedding of material from Phoebe gradually replenishes the E-ring, creating a subtle, ethereal halo around the planet. The gentle interaction between Phoebe and its cosmic environment, resulting in this diffuse ring, is a beautiful example of how even small, captured moons can exert a long-term, placid influence on their planetary systems. Phoebe drifts through space as a quiet, enigmatic wanderer, its dark, ancient surface subtly shaping the distant reaches of Saturn's majestic domain, a silent testament to its unique history and its enduring, unhurried contribution to the cosmic tapestry. Its gentle, persistent shedding of particles creates a continuous, measured flow of material, a serene and subtle form of celestial artistry that speaks to the profound interconnectedness of all things in the quiet vastness of space. And now, the vastness of the cosmos begins to gently fade behind your thoughts. You have drifted through 100 quiet wonders. From the dazzling brilliance of newborn stars to the silent shadows of ancient galaxies. From the intricate web of dark matter to the faint whispers of cosmic background light, you have traveled through starry nurseries, soared along luminous spiral arms, and glimpsed the heart of the universe glowing softly across unimaginable distances. Tonight, We journeyed through the serene and diverse families of planetary moons, from the hidden oceans of Europa and Enceladus to the atmospheric rivers of Titan, from the ancient scars of Callisto to the dramatic tiger stripes of Enceladus. We have observed the gentle dance of shepherd moons, the subtle pull of tidal forces, and the quiet beauty of worlds forged by giant impacts or captured from distant asteroid belts. You have seen how our own moon patiently stabilizes Earth's climate and how new moons are continuously revealed by improving technology. You are part of this cosmic story, not just an observer, but a participant woven into the fabric of stardust and time. The atoms in your body were forged in the fires of ancient stars. The air you breathe carries the legacy of distant explosions. Everything within you shares a lineage with the universe itself, born from the same primordial matter that now flows through galaxies and drifts in interstellar clouds. Tonight, as you rest, the cosmos continues its quiet unfolding. Stars are forming, light is traveling, and cosmic dances carry on in silent harmony. You are a small warm presence within this vast radiant sea, peacefully floating among the stars. Thank you for journeying through the cosmos tonight. I hope you sleep well and dream softly. Good night.